exciting program ahead, packed with a number of really distinguished speakers. So we'll move straight to that. Just a quick announcement I wanted to give. There is a parallel session ongoing on similar matters, status of H0 and sigma 8 tensions and theoretical models and model-dependent constraints. That's the title. The first part was last Monday. Tomorrow afternoon, there will be the second part. So I invite everyone to join that if interested. And then just to tell you that we will finish this plenary session at 7 p.m. Central Time, European Central Time today. And then there will be an half an hour lecture. It's a public lecture on cosmic neutrinos. And then at 7:30 p.m., we will have a roundtable discussion with a follow-up on the discussion that we'll have today during this plenary talks. So I invite George Eustathiou to share the screen, thanking him for joining, and you can start. Thank you.
Okay, well, thanks very much for inviting me to give this talk. So I want to start with the first set of Planck results that we released back in 2013. So this slide shows you the temperature Pal spectrum. The red line is an inflationary, spatially flat cosmology with adiabatic fluctuations, described by 6 parameters that we've come to now term as the standard or basic lambda CDM, 6-parameter lambda CDM model. And on the bottom panel, you see the residuals with respect to the best fit model. The blue points here at high multipoles are band averages of the power spectrum in bands of width delta L equals 30. And you can see that the theory is a brilliant fit to the observations. There are some jiggles that caught the attention of some people. This was actually, this jiggle here at Elec was 20 to 30, was seen by WMAP. But apart from these little jiggles, it's a very good fit. And the Hubble parameter that we deduced from this fit was around 67 or so kilometers per second per megaparsec. And that was really, I think, when it became apparent that there may be a Hubble tension. So that was the situation in 2013. We analyzed only half the mission data for that first data release from Planck. By 2018, which was our third data release, we analyzed the full mission data. This shows you the temperature power spectrum from the full mission data and the best fit 6-parameter lambda CDM model. If you look carefully, there's a slight difference that by 2018, the power spectrum had shifted upwards with a multiplicative correction of 2%, and that was because we now had good calibration of the far field beams of Planck, so we were missing a little bit of solid angle in the 2013 results. But apart from that multiplicative shift, the parameters are essentially identical. Hubble tension persists. And if you look carefully, the residuals at the bottom, it's improved signal to noise. And by 2018, it's an even better fit to the lambda CDM model with essentially the same parameters. Between 2013 and 2018, most of the work on the power spectra from Planck was devoted to getting accurate polarization measurements. And this shows you the 2018 temperature E-mode cross spectrum, again in band averages. And the red line here isn't a fit to these points. It's the best fit model fitted to the temperature power spectrum. And then the residuals shown at the bottom. And for the EE spectrum, again, the red line in the upper panel is what we'd expect from the TT spectrum. As far as parameters are concerned, for almost all cosmologies, the EE spectrum carries very little weight. So the parameters are determined by the TT spectrum and the TE spectrum. So EE spectrum from Planck is really essentially a consistency check. Okay, so now that was the situation at our 2018 data release. And at various times, people have pointed out odd aspects of the Planck spectrum. So one of the odd aspects that has attracted some attention is that the Planck temperature power spectrum seems to be slightly smoother than you'd expect in the 6-parameter lambda CDM model. And if we multiply the effects of lensing by intervening matter by a phenomenological parameter A lens, AL, then so this parameter is normalized so that it's 1 if the lensing is exactly as expected in the 6-parameter lambda CDM model. What we found from Planck is a value that's slightly bigger than 1. So that was an anomaly, and the question was that telling us anything? A very closely related anomaly is that the Planck data favored closed universes. It has been argued that the high multipoles from Planck give different parameters to the lower multipoles. Various people have pointed out jiggles in the TT spectrum that I mentioned earlier, and also anomalies in the TE spectrum. So a number of anomalies, none very significant, all in the sort of 2.5 to 3 sigma range of statistical significance. But these were left pretty much, they were left open in the 3rd data release from Planck. So a number of anomalies at the sort of 2.5, 3 sigma level. So what I wanted to do, when we'd finished the 2018 set of Planck papers, was to investigate some of these anomalies in more detail. That's what I want to discuss, and this is work done jointly with Stephen Grattan. And here's the basic test. So X here is the mean of independent random variance with zero mean and dispersion of unity. So as we increase n, then the mean will tend towards 1. So what I've shown here is a series of random walks, which just shows what happens if we increase n. You get trajectories. So this trajectory here, for example, this crosses the green line, which denotes 3 sigma deviation away from what we would expect. And then it comes down again. Okay, so now I've only shown about 200 trajectories here. What I now show you is what happens to trajectories which hit 3 sigma before n equals 50. Okay, so all of these trajectories are above 3 sigma when n equals 50. Then you see by the time n equals 100, most of them have come down in statistical significance. In other words, if we have a 3 sigma discrepancy, a relatively modest improvement of the power of the data will, if it's just a statistical fluctuation, statistically the significance level will drop with a modest improvement in the statistical power of the data. So that's the test. If there's anything, if we have a number of anomalies or anomalies at the 2.5, 3 sigma level, then if we improve the quality of the data, we don't have to improve the quality of the data enormously, then the statistical significance of these things will statistically become less statistically significant if there's no, if they're not reflecting any real deviation from our theoretical model. So that's the test. So to achieve that, here are the Planck frequency maps. To achieve that, what we did was we focused on the high frequencies. So here's 143.217, and used 545 gigahertz to subtract dust. Okay, so we use 545 gigahertz to subtract dust in temperature, 353 gigahertz to subtract dust in polarization, because the 545 gigahertz channel is not polarized. And the key thing, though, is that in temperature, you have essentially a noise-free dust template, which you can subtract from 143 and 217, and that takes out the dust contribution. So here's an example. So here's the raw 143 gigahertz map from Planck. And here's what it looks like cleaned with 545 gigahertz. And this is one of the more complex component subtracted maps produced by the Planck team. The thing is that this is a very, very simple thing. It's just a single coefficient, and it produces science grade data. You cannot really distinguish these maps with the component separated maps at above a few degrees from the galactic plane. And if you do this, then 143 becomes the cleanest CMB map from Planck. If you try this with 100 gigahertz, then you see residual synchrotron and CO emission at low galactic latitudes. Okay, so that's the test. We subtract dust and we use more sky area than used in the Planck papers, and that improves our signal to noise. So to show you what happens, here's the Planck spectrum as it is in the 2018 papers, and then the new spectrum. And I think that you can easily see that the residuals have gone down. And just to emphasize this point, this shows the residuals on an expanded scale. So what we found from this test is that wiggles, jiggles, and anomalies like A lens improved when we increased sky coverage. So the statistical significance of anomalies decreased. Not one anomaly that we focused on from the 2018 analysis got worse with this, okay? And almost all of them got better. This shows the intercomparison of the spectra that we used to make a more powerful likelihood. So this is 143 cross 143 minus 217 cross 217, 143 cross 143 minus 143 cross 217, and then 143 cross 217 minus 217 cross 217. And these are the residuals in the range 500 to 1500, which is for the base lambda CDM model. That's where most of the information is coming from that constrains parameters. And this, nothing like this has ever been seen in a CMB experiment at this level of consistency. They're in agreement to within a 2 or 3 microkelvin squared. So what does it do for parameters? Well, the answer is not very much, not for the base model. This shows you the parameters of the base model plus a few other parameters like S8 that weak lensing is sensitive to. But if we focus on, say, the Hubble constant, this is the Hubble constant here in the physical baryon density here, then this is what we get with the 2018 Planck analysis, and this is what we get with the new analysis. Okay, we used more sky area in temperature and in polarization. And basically what happens is that the TE spectrum comes into closer agreement with the TT spectrum, and the blue contours, which are everything combined, stay more or less the same. So there's nothing wrong with using the parameters in the Planck papers. This has not changed things very much. It's just, somewhat improved the consistency between the various spectra for the base lambda CDM model, but you do see movements when you look at extended models. So here's an example. Here's the A-lens parameter. And so this is the expectation of A-lens equals 1. And this is what we get. Okay, the blue contours, everything combined. What happens here is that there is a pull towards values of A-lens greater than 1 with TT. The polarization is quite neutral and is not very constraining, but it's enough to lop off these high values and bring you closer to A-lens equals 1. And the discrepancies in the low 2 sigmas, 2.2 sigma or something like that. It's not a very significant discrepancy. Likewise with curvature, the problem with curvature is there's a geometrical degeneracy, and the Planck data, because of the geometrical degeneracy, the spectra allow you to sit on a very extended degeneracy line. Here is a spatially flat universe. So you need something to break the geometrical degeneracy, and this shows what happens as you use increasingly more constraining supplementary data to break the geometric degeneracy. First with Planck lensing, CMB lensing, then adding in supernovae, and note the change in scales here, and then finally, if you add in baryon acoustic oscillation data, the constraints tighten up very, very closely to a spatially flat universe. If we don't include any other data, then adding curvature as a parameter improves the TT-TE chi-squared by only -3.02. So it's a very small improvement from the high multipoles. So you're the dependence of chi-squared along this degeneracy line, it's incredibly flat. So this shows what happens with extended models. And now you can see, I think, visually what's happening with these extended models. So the best fit A-lens model, you'll see that because the degeneracies are very flat in A-lens and omega curvature, that these numbers are the best fits, and the best fits differ quite a bit from the means of these parameters. So, but you can see that these extended models, they're responding to the same jiggles, pretty much, and that's why you get results that differ, from a spatially flat universe and A-lens equals 1. But these deviations are not very statistically significant, and the change between the 2018 results and the 2020 results, they're consistent with what you'd expect if the 2018 results were statistical fluctuations. Okay, so now if we now look at the polarization spectra, so here what I've shown you is the polarization spectra measured by Planck, and then with ACT-DR4, the recent ACT data release. So this is the TE spectrum, and then the residuals plotted here. Then the red line is our best fit from Planck TT-TE to the base lambda CDM model. And you can see that at high multipoles, it provides a very, very good fit to the ACT-DR4. And then SPT3G announced their results quite just recently, and here are the deviations. Okay, there's no evidence for any deviation from the base lambda CDM model, and then this is for the EE spectra where Planck is really not very constraining, and then you see with ACT extending to high multipoles is very consistent with the best fit model from Planck, and likewise with SPT3G. So I think that the situation is that lambda CDM provides a brilliant fit to the CMB observations from Planck, and now ACT and SPT. So as far as the Hubble constant is concerned, I think that if there is a Hubble tension, then it's not the fault of the CMB experiments. I think we were justified in reaching that conclusion. Now, so here is a summary of the Hubble tension. I'm running out of time, so I'm not going to say too much about this, but I want to emphasize three things that you may not know about the Hubble tension in extremely telegraphic language. Okay, so the first is the difference, and really, if Wendy disagrees with this, she can say so. So the first is the TRGB comparison, the tip of the red giant branch comparison with the Cepheid comparison. And so I think that this difference is a calibration difference because, as Wendy's pointed out, both groups can measure relative distances extremely accurately. This shows the distance moduli plotted against the supernova apparent magnitudes. And here I've used exactly the same supernova data and exactly the same geometric distance anchors. So this is using the LMC with detached eclipsing binary constraints on the distance to the LMC. So this shows you with the tip of the red giant branch measurements. With this, I got a Hubble constant of 70. With the Cepheids from shoes, I got a Hubble constant of 76. So that's the difference between the Cepheid and the TRGB distance scales. So there's a difference of 6 kilometers per second per megaparsec. But this error here is dominated by the error in the supernova magnitudes. And here I've used exactly the same supernova magnitudes. So the aspect that Wendy pointed out was that the difference between both groups are measuring relative distances extremely accurately and consistently. It's just that they're offset. And they're offset by 0.14 magnitudes in this case. So the difference, I think, between these, the TRGB and the Cepheid distance scale is a calibration issue. And obviously, the TRGB calibration is consistent with the Planck value for lambda CDM, but the shoes calibration is not. The other thing that aspect that hasn't been emphasized but has worried me is that with the shoes Cepheids, the distance anchors are in tension with each other. So if I combine the LMC, the Maser distance modulus for the Galaxy NGC 4258, and use the Gaia DR3 parallax measurements of Milky Way Cepheids, if I combine them all, I see an inconsistency between the best fit distance modulus for the LMC and for the Maser distance modulus compared with the geometrical values. So when you see diagrams like this, which show variations of the Hubble constant for different combinations of distance anchors, you should be very wary because these motions, these movements, are reflecting tensions in the distance, in the geometric distance anchors themselves. So I think that's a real worry. And then the third point that I wrote about recently. So here I've shown HZ divided by 1 plus Z to the 1.5. Here are the baryon acoustic oscillation measurements from galaxies, from quasars, and from Lyman alpha absorption lines, normalized using the Planck value of the sound horizon. And then this is what we would expect to see for H of Z from Planck. To match the Cepheid result, then I need to get something like the dotted line. So I'd have to have, if I'm doing this with dark energy, so I'm using some sort of change to the late time physics, then I have to have phantom light behavior. And and the thing, I think this is incontrovertible, that an inverse distance ladder just does not allow that kind of solution. So I don't think that you can solve the Hubble tension by changing the expansion history at late times by any means, whether you have phantom dark energy or interacting dark energy and dark matter. And if you do an inverse distance ladder, then the red line is what the Shoes team, from Cepheids, what they actually measure that goes into giving you a Hubble tension. The black is what you get from an inverse distance ladder, and they're discrepant. If you turn it into a Hubble constant, then an inverse distance ladder gives you 67.73, completely consistent. So anyway, to conclude, as far as I can see, and with an extended analysis of lambda CDM, my conclusion is that lambda CDM fits the data perfectly within acceptable statistical errors. And believe me, I would have loved to have found a statistically significant deviation from lambda CDM. So, if your experiment disagrees with Planck, then either the experiment is wrong or we have uncovered new physics beyond lambda CDM. The problem is not on the side of the CMB. And then if you have a physics explanation, any new physics has to produce temperature and polarization spectra that are degenerate with the 6-parameter model over the multipole range now 2 to about 4,000. So any evidence for a deviation from basic lambda CDM is strongly dependent on the fidelity of other data. And it's not just because I'm a miserable individual that I keep pointing the finger towards other data. I think that's actually true representation of where we are in the subject. So thank you very much for your attention.
Thank you very much, George. Okay, I just see if there are questions, please post them on the Q&A. If you are not able to join directly the meeting, can you read them, George, on the Q&A?
Yeah, that now okay. It's my proficiency at
or otherwise
Zoom. I can if I stop the share.
Sure, you can.
Okay, if I stop the share, let me do that. Right. Okay, so I've put chat on.
The Q&A on the right.
Oh, Q&A. Okay, yeah. Okay.
You have an improved plot available to start.
Right. Okay, so if I just read them out, do you have an improved plot of A lens versus tau? Yes, we do, and I can send you the I can do better than sending you the plots. I can send you chains so that you can explore relations yourself.
Okay, so we have more questions. Kind of one on.
So this question about modifying the matter content at late time does not modify the evolution.
The evolution.
Well, of course it does. Okay, but the point is that you've got to, in the way that an inverse distance ladder works, you have to. I mean, I'm assuming the Planck value of the sound horizon. So there's no change to the physics at early times. The sound horizon is consistent with what we infer from Planck. And then you have to explain the BAO data and the magnitude redshift relation of the Pantheon supernova sample. And I'm saying that is strong enough. And I don't think there's anything contentious here. That's strong enough that it really rules out large changes to the expansion history. Certainly, changes that are large enough to account for a nearly 10% difference in the value of the Hubble constant. Right, is there any new insight on the suppression of the quadrupole? The answer is no, unfortunately. When we got the first set of results from Planck, we saw exactly the same large angle, temperature fluctuations that WMAP measured, and the anomalies, you know, of the quadrupole, you know, correlations between the you know, sort of so-called axis of evil, that there's some sort of correlation in the orientation of the low order spherical harmonics of the CMB. All of those are exactly the same as with WMAP.
Okay. Then can move on to the next question by Joao Luis.
Right. So, yeah, I mean, what I referred to was, you know, changes to the expansion history in the context of you know, Einstein's general relativity. So if you start modifying gravity, then that's beyond the scope of this talk. And
okay.
Do you think that the anchor inconsistencies could be the result of unaccounted local inhomogeneities? So no, because the anchor distances are, you know, they're geometric distances. They don't depend on the metric. There's no assumption of homogeneity in deriving the anchor distances. So it's something else. Okay.
Okay, so there is actually Wendy Friedman has a question. You can unmute your mic and.
Yeah, George, you asked if I disagreed with you, and I understand you might not be staying, but the short answer is no, I don't disagree with you. I think right now, as you correctly characterize, we have very good measurements of relative distances. We're agreeing well. The issue is in the absolute calibration, and I think there's still movement there, as you've shown. And that is, we may characterize it by different language, but that we're seeing the same thing.
Yeah,
and
yeah. Sorry, Wendy, yes, you go on.
Yeah, no, that's basically what I wanted to say.
Oh, okay, so it's interesting because, you know, I think that you know, I mean, I've written to you and I've said that, you know, I think if we could solve this problem, we'd probably solve the difference between, you know, the two groups. You know, I think that's where we need to focus. But you know, I'm worried by the fact that, you know, I mean, 0.14 magnitudes is big. So I don't think it's as simple as, you know, dust in the LMC. You know, you may get 0.05 or so from dust, but 0.14, I mean, you know, after all, you know, the difference is, you know, we're arguing for, you know, a few percent difference. So it's quite a large difference that we're looking for.
Yeah, I agree. And I think right now, what we're stuck with in the local universe are very few nearby galaxies or, you know, objects within our Milky Way where we can get geometric distances, and we're stuck with that small sample. But everything hinges on the absolute calibration, and that's still in motion. I mean, so if you look at the Large Magellanic Cloud, you know, the new photometry has suggested that the Hubble constant comes down for the Milky, or goes up rather, for the Milky Way. The Gaia current parallaxes suggest that it comes down, and things have sort of settled in the middle around 73, but they are in motion. And I think that's something that we need to pay close attention to. There is tension, as you point out, if you calibrate the Cepheids with the LMC compared to whether you calibrate with the Maser galaxy NGC 4258. So metallicity also comes in as an uncertainty in the Cepheid calibration, and that's something I think that we need to pay close.
It does, but it doesn't between Milky Way Cepheids and NGC 4258.
Agreed, but then it disagrees with the Large Magellanic Cloud. So there's tension between the different anchors, depending on what you take for the correction due to metallicity.
Right.
Okay.
I think we're just in agreement.
Yeah, we are. I mean, you know, in those, you know, one of the things that worries me when you have a tension like that and you do a global fit, then you become the tension itself. You know, can you believe your solutions for metallicity, because they will be pulled in a direction to try and resolve the tension. So, you know, It's not obvious that those are really measuring metallicity when you've got tension like that. Okay, so that's enough.
I think the Planck team has set the bar really high, and I think the challenge is to make the measurements locally that can get at differences at the percent level. And the reality is that measuring distances, measuring relative distances, we're doing well. It's a huge improvement, but measuring absolute distances at that level of accuracy needed to test Planck is a tall order, and still in progress.
Good.
Okay, I think we probably need to move on. Well, thanks again.
Thank you.
And I guess, we will continue this very discussion with the next talk by Dan Skolnick, which is on new determination on the Hubble constant with Gaia DR3 and further evidence of excess expansion. So Dan, are you?
Yep, I'm here. Could you just let me share my video? It says the host needs to let me.
Thank you.
Still not. Oh, it says the host has stopped it.
Okay, we'll read the questions later on because
I'm happy just to start. You don't have to see my face. It's
right now I'm just saying that. I just realized that the audience doesn't see the Q&A questions, so next time we'll need to read them. Correct. Thank you. I'm sorry for that. Okay, go ahead.
Okay. Oh, now I'm getting asked to start my video. Okay, great. So I'm just going to share my screen. Okay, can people see this okay? Guess so. All right, so thank you for having me. So Adam Rees was supposed to be giving this talk, and I'm a bit of a late-minute substitution. Adam is in the desert somewhere with bad internet connection. So this will be a little bit different from the talk that maybe Adam would give on the Shoes team. Adam's kind of main focus on the Cepheid side, my main focus on the supernova side. So this will be tilted a bit more towards supernovae, but I'm going to try to cover a number of Cepheid things as well. Okay, so George has kind of covered this a bit, but just as a really quick overview, for the local distance ladder, it's 3 steps where in first step, using some kind of geometric calibration to calibrate Cepheids. In the second step, you're using Cepheids to calibrate type 1a supernovae. And third step, you're using type 1a supernovae to calibrate redshifts. So the Shoes' latest results is H973.2. So this is, as everyone knows, about a little over 4 sigma from Planck and with Lambda CDM. And that's why we're here. Okay. Now, my goals today will be to just quickly discuss the type 1a supernova component of the distance ladder. Then I'll cover the Cepheid component of the distance ladder, and then I'll try to go over some of these differences between Cepheids and TRGB that George was just talking about. All right, so I'm going to start with the supernova part because what's nice about type 1a supernovae is that you basically can use the same sample to measure dark energy or omega matter, other cosmological parameters, as you use for H9. And the difference really is that you're comparing supernovae at Z of 0.005, really close, that are in galaxies with Cepheids, to supernovae a bit further away, Z of 0.05. And for W, basically comparing supernovae at Z of 0.05 to supernovae at 0.5. So this is showing in the middle the Pantheon sample. So this is kind of the largest homogeneously calibrated sample to date. You can see kind of flanked on both sides is the sample used to discover the accelerating universe. And you can see just kind of how much better things have gotten, but in a very kind of straightforward way. So supernovae really have held up quite well. Now, as George kind of mentioned, we are looking really good for a cosmological constant. So we measure W equals minus 1.26 plus or minus 0.04. And really, we kind of very weak constraint on WA. And I think kind of these next samples, some of which I'll talk about, will start to really constrain that. Okay. Now, one thing that we've looked at, so this is a paper led by Suhail Dewan, is can you have different kinds of kind of late universe modify dark energy type thing to change the Hubble constant? And pretty much the answer is no. There's some jiggles, as George would call it, in the Pantheon data set. Those are mostly due to systematics. And even with them, you're just kind of not changing H0 beyond 0.5% kind of from the supernovae. And now kind of it's not just supernovae that are holding up this strong evidence for dark energy. We have multiple probes, as you can see on the right. Okay, so that was Pantheon, but kind of what's coming up next is from work that I'm doing with Dylan Brout, who I think is on this call. And we're really increasing the sample. So it's from 1,050 supernovae to 1,700 supernovae. And what we're really working hard on is that you could use the same supernova sample for the W measurement as the H0 measurement. So if you want to kind of do any kind of big late universe thing altogether, you can. And we have kind of many samples. You can see the kind of agreement on the right. This is a big zoomed out version because I don't want to show the answer yet. But you can see the calibrator supernovae and the Hubble, the kind of Hubble flow and beyond supernovae. And you could kind of do any type of analysis with all of them combined. And that's going to be really exciting, I think, for the community. So we now have this covariance matrix that relates all the supernovae used kind of for H0 to the supernovae used for W. We kind of have this unbinned covariance matrix, and I think this will open up a lot of new studies about any kind of very late term modification to your cosmology that you might want to do. So this is based on a couple papers looking at covariance matrices. Okay, now there's still a number of papers about supernovae that are saying somehow you can use supernovae to not get dark energy or strange things like this. So these are still popping up, once a month or so. And so these are plots from a paper by Dylan Brout that's showing kind of the level of validation with simulations we now do for our samples. So kind of we're validating every property of our supernova surveys, the weather histories. And then we're using that to kind of correct for any possible selection effects. And the studies that are coming out, they're saying something really strange about supernova samples are typically ones that just ignore all of this, try to do their own thing at the end, and then get some strange thing out. So we release these simulations so people can validate their own studies. And I really kind of encourage that to happen. Okay, so there's been a number of papers that have tried looking at the supernova side to say there's something wrong with H0. One is something to do with kind of the redshifts of supernovae. The other is kind of has to do with host galaxies, and I'll quickly hit those. So the first has been papers pointing at some big anisotropy with supernovae. Part of the reason that we're kind of vulnerable to this is that our supernovae were preferentially discovered in the north. So you can see this in this plot on the left here. And kind of just over time, as our sample is getting bigger, that's decreasing. And there's really just kind of not much room for cosmic variance to have a big effect on H0. So kind of on the theory side, it's supposed to be about 0.6% H0. And really what you'd be looking for in these Hubble diagram residuals is some kind of dip, some void. And we just don't see any evidence for that. So I've never been able to reproduce any of the results kind of pointing at some big void or anisotropy. One other thing that people have said is that maybe there's something wrong with the redshifts. So there should be 2 new papers coming out, basically a full comprehensive review of all the redshifts we're using for the supernova samples. In the end, maybe this is a couple factors like 0.2 and H0, but really this is looking to be pretty small, and those will be out soon. Okay, so the other thing that's going to point out is that, well, there's some relation that gets a lot of attention that has not been standardized for with type 1 supernovae between the luminosity of supernovae and their host properties. And this has been just this big mystery in the type 1a supernova community. Why does it seem that Hubble residuals correlate with properties of the host galaxies? There's some kind of floor to how well we could standardize, and what's the deal with color? So this paper with Dylan Brout that we did in this last year, we basically can explain all of this with kind of varying dust properties in galaxies that depend on the properties of the galaxies. So kind of with one swoop, we kind of can explain all these big mysteries in type 1a supernovae. And this is kind of basic, goes back to this idea that was in the community 15 years ago that's now since been moved away from, but we have with these big sample, these 11 and 8 sigma effects. So we have a really good constraint on the different components of supernova color, whether it's intrinsic and dust. And this is going to come up for the Cepheid component in a few minutes. But what's nice is that we could basically answer these different mysteries. So this is showing on the bottom panel the kind of now famous host mass step. We show that it depends on color. We could explain this as due to different dust properties in different galaxies. And while I'll say kind of this, we're really proud of this, and this is really cool, they could answer all these different questions. In the end, this changes H0 by about 0.3. So for a total kind of re-envisioning of how supernova physics works, the impact on H0 was about 0.3. And so that kind of shows how sturdy this is. I'll just say kind of there's this paper that came out, Johansson et al. That really agrees kind of nicely with this result. So I think we kind of have a much better lever arm now on how type 1a supernova standardization works. And there's a lot of things that are going around before of like maybe it's some age or progenitor issue, and now we just don't see that to be the case. So we can constrain this really well. Okay, and I'll just kind of wrap up with the type 1a supernovae to say that, as George mentioned, you could use type 1a supernovae to go backwards. And if you use baryon acoustic oscillations, you get low H0. If you use kind of the earlier strong lens results, you get high H0. So basically supernovae will kind of move whichever way the something else is anchoring it. So it'd be very hard for supernovae to be kind of push something one way, another thing the other way, if supernovae were the problem. And just to kind of beat that in, if you replace type 1a supernovae by surface brightness fluctuation measurements, or even by a kind of worse kind of standard candle, these type 2 supernovae, and you use, this is using Cepheids or TRGB, you're getting a high value of the Hubble constant. So it's kind of, it seems less and less that it's the supernovae that could be doing this. Okay, so now on transition to Cepheids, and basically where the different uncertainties are hiding. So there's these 3 steps, and the first step you have multiple anchors, and I'll talk about that in a minute. The second step is really where we're kind of pushing down most on our statistical uncertainty. So this is the number of galaxies that you have with supernovae and Cepheids. And the last step, this is basically like the Pantheon sample. This is the Hubble flow, where you're really kind of, you're mostly affected by supernova systematics. Okay, now for the anchors, which I think we're all kind of agreeing is where the focus should be. For SHUs, there's these 3 different anchors. There's parallax, good to 1%, detach eclipsing binaries, LMC, good to 1.2%, and masers in NGC 4258, good to 1.5%. So kind of all kind of on the kind of 1-ish% level. So all with different independent votes. Okay, now the different values of H0 that you get are 72 for NGC 4258, 73 for Milky Way parallaxes, and 74.2. And I'll talk about this more in a little bit. I don't see the kind of reason to think that there's tension here. And I don't know, if I were George, I'd just call this a jiggle and a wiggle. But this is kind of where things are at. Okay, and then we have a number of checks of either kind of different smaller samples of Milky Way parallaxes, and you can see this kind of range here from 72.7 to 76.2, but all with kind of 2 to 4% uncertainties. Okay, so how do we improve the first rung of the distance ladder? And what's really neat is that you can use Gaia. So kind of Gaia has been used by the SHUs team in 2 ways. Kind of first is on the Cepheid side, and second is on the TRGB side. I'll only talk about the Cepheid side now, and I'll get back to TRGB side in a minute. But just to kind of show you how much better the latest release of Gaia is. So this is Gaia DR2, and this is comparing the Gaia DR2 parallax on the y-axis to the predicted parallax using the kind of fluxes and periods that we've measured. So this here is DR2, and then I'm going to click now, and that's EDR3. So you can see just going back and forth. So just an enormous improvement on Gaia's part. And here you get applying it with type 1a supernovae, H naught of 73 plus or minus 1.4. So it's really kind of strengthening this particular anchor. Okay, now there's been a lot of discussion about different Cepheid systematics, and I want to try to quickly go through each one of those. So first one is, could Cepheid physics be different locally versus more distant? What's the impact of Cepheid crowding? Could Cepheid photometry have gotten messed up? And could measurements be sensitive to dust? So the first one is, could Cepheids kind of very locally be different than Cepheids a little bit further away? And so here, this is showing the Cepheid light curves for the ones. This is basically a composite diagram, so a bunch of Cepheids stacked together in type 1a supernova hosts versus in the Milky Way. And you really can see the same, all the kind of same physics. So same what's called the Hertzsprung progression, the same light curve structure, same physics, and same fundamental asymmetry, 2-to-1 resonance overtones. So kind of if there's something that should be just different in Cepheids, something very nearby versus kind of a little bit further away, something should show up here, and there's just nothing showing up here. And kind of there's these concerns about metallicity, but they appear consistent across the distance ladder, and they're marginalized over. Okay, so the second question has been, well, to measure Cepheids, there's a lot of blending, and that makes the photometry particularly tough. So kind of what Adam does are these fake star injections. And there's this really nice paper last year that basically showed that you could predict the exact effect on the amplitudes of your Cepheid photometry by the amount of crowding that you measure. And so there's kind of just a zero parameter prediction if you're that you can then compare against what you get. And basically the takeaway here is that the prediction, if you're doing it right, should go through the red bins here, and you can see this kind of really good agreement. So this is kind of a proof that crowding should not be or is well accounted for in the Shoes analysis. Okay, and the third thing has been, okay, well, still the photometry is really hard. So, are you doing the right thing? And there's this really nice paper by Java and Marty et al. And this is in the archive where they do a really in-depth look at one galaxy. So this is, basically they chose the richest galaxy. So there's nothing particularly weird about this galaxy. It's supposed to be kind of just a normal galaxy, but just had a lot of Cepheids. So you could do a lot of different. And basically there was to try to do every analysis choice different than how Shoes did it. And not because those things were better, they just wanted to do it because it was different. And they get really great consistency. So 0.024 plus or minus 0.046. So really no differences in the photometry. Now, kind of one thing that's been pointed out after is like, okay, well, this is just one galaxy. And I'll just say that kind of Wendy Friedman has led these nice results kind of before working on TRGB, which kind of the HST key project, and they get a high value of H9 of 74 plus or minus 2. So this kind of thing of maybe, there's just not enough independent confirmations of kind of going to some level of the analysis, that doesn't seem the case to me. Okay, now the latest thing, and this kind of new, is this paper that tried to explain all of the Hubble attention due to dust. And basically this group was using the paper that Dylan and I did as motivation. They said, okay, well, if supernova dust can be weird, maybe Cepheid dust can be really weird. And basically, if you kind of see, so they titled this paper, The Hubble Attention Bites the Dust, which I thought was kind of sensationalist. But they really kind of have two different methods, one of which is blaming things on dust. And that's the one where they get H0 of 71.8 plus or minus 1.6. Actually, they do something very different that has nothing to do with dust, where they change black body physics. And for that, you could get H naught of 67, but you're really basically, you're completely changing fundamental physics. And I think after this paper, the team kind of has really backed away from this number, but still thinks this kind of the dust way is possible. It's where you could get a bit of a lower value of H naught. So just to explain this really quickly, so when you do a correction for the color of Cepheids, just like for supernovae, there's some intrinsic part and then there's some dust part. And in how Shoes has been doing it, you basically combine those two components. Now, if you want to say, okay, well, maybe dust can be weird, then you have to separate the intrinsic part from the dust part. So this is just showing in this equation here, this separation of the kind of the physics part versus the dust part. And if you do that, you get these kind of different values for your reddening for all your different galaxies. Now, the big thing I want to point out is that you could see really small uncertainties for the calibrator galaxies, and basically much bigger ones for ones further away. And this is just because you have much better signals to noise and less crowding for things that are nearby. So effectively, things further away are getting the prior, and things nearby are not getting the prior. And that's actually what changes H naught from 73 to 71.8. So I'd say more of this is kind of not the best way to do the analysis because you're not accounting for how noise affects the color that you're determined. Now, the other way to do it, I think, is kind of definitely not right. So this is, you're basically saying, I'm forgetting that there's different components. I'm just going to combine the dust intrinsic part. And effectively, because of convention of kind of the color of Cepheids, you're mostly then just changing the physics of Cepheids, basically how the black body temperature relation works. And if you do that, then you could get this low value of the Hubble constant. But if you want to throw out kind of black body physics, then yeah, I mean, then Cepheids just are not any kind of standard candles. And I don't think anyone really wants to do that. So maybe this is a bit of a systematic, but it's certainly not biting the dust here. Okay, so finally, I'll just get quickly to this question of well, how well do Cepheids and tip of the red giant branch agree? And I have not seen a number as high as 0.14 mag as what George was showing, so I'd like to do that one. But what I have seen is something more close to 0.06 mag. And you can kind of see this a little bit by eye. This is in one of Wendy's most recent plots. And I think, and maybe we all agree that this implies some kind of calibration difference, most likely in the first rung of the distance ladder. The supernovae kind of agree, the relative distances, like you don't see any kind of slope here to this plot. It looks kind of mostly like an offset. And I think this is kind of one of the most interesting questions we have now. This is something that I'm sure Wendy will discuss, but there are different measurements of the tip of the red giant branch. So the CCHP team is, I think, the leading team on this. And you can see that for the kind of measuring the tip, they are getting this number of minus 4.05. And just for kind of shorthand, that gives you H naught of roughly 70. And then if you get minus 3.96, then you get H naught of 73. And kind of if you look at CCHP team results, they're typically at minus 4.05. And then just calling them kind of Shoes-ish. This is from a compilation in Blakesley. Shoes-ish, I just mean like someone from Shoes was on that paper. Those are typically at minus 3.97, and then others are more in between. So, I think that this is a really interesting area of study. Now, one of the recent papers that had a number of Shoes people is trying to calibrate tip of the red giant branch using the parallax of Omega Centauri. So this is a paper by Soltis, Casatano, and Rees. So this is using Gaia, and this is the best direct Milky Way tip of the red giant branch measurement, where you have 67,000 stars and can measure really tight locus. And looking at the parallax as a function of Gaia G-band, you really don't see any noticeable systematics. So to do that, you get this m sub I minus 3.97, and that gives you H naught of 72.1. Now, there's been a number of Gaia studies kind of on this that get generally good agreement. And I think the big question now is this uncertain? How good is this uncertainty? So there've been some papers that have said this uncertainty is too small. There's been another paper that said it's too big. And understanding the Gaia systematics is going to be one of the top questions now. Okay, so lastly, I just want to say this thing about consistency, and this is kind of where I will push back a bit. So this is just a plot from Wendy's last paper, and I think that I just want to be very careful about picking what's better due to kind of looking at the number, the values of H naught you get from different anchors. So this is showing different H naughts from the different anchors for both TRGB and Cepheids. And one thing that you heard George kind of picking on is like with Cepheids, okay, there's some little differences here. And statistically, I think you should expect some differences that should happen. Whereas something like TRGB, you could see there's much smaller differences. So this makes me nervous to kind of go too far in one direction, because we could go in the other direction. So I just want to show this other plot. So this is just taking the same table from tip of the red giant branch and plotting it, just showing it in plot form. And so this is the tip of the red giant branch versus the anchors. And here things look super good. But I'd say, the chi-squared is 0.05 over 4, which is a 4.3 sigma chance of kind of luckiness. So I'm nervous to go either. I play this game either of these ways, where you say, oh, there's a little bit of disagreement that makes this one better, versus if you want to say, hey, this is such good agreement, well, that's the same level of chance that is the Hubble tension. So I think that we kind of need to have more time, more eyes on the Cepheids and the tip of the red giant branch, and not just kind of look at these final things and say that should determine which one is right. So hopefully we kind of all agree that these things need more time, more attention, and that's what we should be doing. Okay. All right. So lastly, I'll just say that what can we be looking forward to in the coming months? First, kind of there'll be this new Pantheon Plus and new shoes papers. So Pantheon Plus will have these joint H naught and W analyses. For shoes, we'll be increasing the Cepheid supernova calibrators from 19 to 42. We went back to all the pixels, new HST calibrations, new Cepheids in NGC 4258. And that, I think, will actually make some of this NGC 4258 disagreement better. And I think George has actually seen some of that already. So this goes from 150 to 500 Cepheids. New metallicity measurements, lots of analysis variants. And then kind of in the longer term, JWST will hopefully launch and be okay. And that will reobserve the richest hosts. And that will really help with resolution, looking at crowding and everything like that. And finally, I just want to say that, we kind of, the focus has become on the Cepheids versus TRGB, or those two, but there's still a lot of other anchors and a lot of great work being done by a lot of people. Surface brightness fluctuations, Tully-Fisher relations, and those keep getting better. And you can see kind of where those are lining up on this plot here by Di Valentino et al. So I'll stop there and happy to take any questions.
Thank you very much, Dan. So there was George actually who had a comment. So I invite him to come online and give a comment. In the meantime, would you mind to go through the Q&A questions, and then after George's comment, you'll try to answer those, possibly reading, I can do it, but or reading the questions, since the audience cannot see it. Okay, George, are you?
Yes. Hi, Dan. So look, I mean, when you quote a value of H naught now, with the error is typically 1.4 kilometers per second per megaparsec from shoes, and that is, I mean, that error is dominated by the supernova magnitudes, not the errors in the distance moduli from the Cepheids. Okay, and my point about the shifts in these inconsistencies, the distance anchors, is that you can, the differences between distance anchors, the error is much smaller than the 1.3 kilometers per second per megaparsec, because that has nothing to do with the supernovae. So small shifts can be quite statistically significant. And that's my point. So when you look at the overall error budget, they're correlated errors between the distance anchors, and you should take that out. So what you should do is just focus on the differences in the distance moduli. Forget the supernovae, forget H0. And then you'll see that the errors, the differences between the distance anchors, I think are worrisome, okay? And that's my point. And incidentally, that is what accounts for the 0.14 difference between the TRGB scales and the shoes scales, because I'm using only the LMC distance anchor. So there's no error folded in, for the geometric distance anchor itself, because it's the same. And I'm not diluting it down by adding in NGC 4258, which reduces the size of the discrepancy. So the difference between 0.06 and 0.14 is adding in 4258. That's my claim.
Yeah,
It's unarguable. Okay, I mean, you can just calculate this.
Right. Yeah. We've messaged. I think we're in a good amount of agreement about kind of, how to do this backwards. I just have not seen, doing the calculation, anything more than like, I don't know, 2.3 sigma for the most disagreeing shoes anchors. So
the plot in my talk, the difference is 3.7 sigma.
I haven't seen anything that big.
Okay, so yeah, so I think
and even with that, I mean, the biggest disagreeing thing is NGC 4258, and
yes, that's right.
As I think you've seen, that has kind of joined the pack more in this next analysis.
This would be very interesting to see. Okay. Yeah.
Yeah. Okay. I think I have a number of questions. So
a number of questions to speak. So we have still, well, we do have 4 minutes. So
4 minutes.
Yeah.
Okay. So should I just pick some of the questions?
Sure. Yeah.
Okay.
First one on
So we see a huge dipole in the CMB, presumably because our galaxy and the local group have a significant velocity relative to the Hubble flow. Should this not give a small but perhaps significant boost to supernovae in directions close to this dipole? Yes. We account for the CMB dipole in what we call kind of our peculiar velocity corrections. And this does effectively increase our value of H0 by about 0.5 kilometers per second. One thing that we do is if you take a higher minimum redshift for the supernovae, then you're less sensitive to this. But yes, this is part of it, and we'll have a new paper that kind of goes through the impact of this very soon.
Okay, could you go further up the questions earlier on?
Oh yeah.
There's one about the possible contamination of overluminous supernovae.
Right. Okay. So for overluminous supernovae, there are different kinds of potentially overluminous type 1a supernovae, but what we do is we essentially cut our supernovae based on certain properties. So what we kind of call the normal properties, and that makes our supernovae very kind of homogeneous. And so we now have these samples of thousands of supernovae, and the number of these kind of I think these overluminous supernovae are on the level of 1 or 2%. So they're just given that they'll have some big uncertainty, and they're just 1 or 2 supernovae, they just won't pull things quite enough to have a significant effect.
The next question directly to you, Nicole Kane.
Okay, yeah. Would you say that TRGB versus Cepheus is just a technical problem for astronomers? SBF, Tully Fisher, and Megan Mazers all seem to agree with shoes. I don't know what a technical problem means, but I guess I could say I'm glad astronomers have stuff to do and get to play a role in cosmology. I think that's good. I think that for all these points, what's difficult, and this kind of goes back to what George is saying, is trying to take out any kind of double counting of uncertainties. So with a lot of these different measurements, whether it's TRGB or Cepheus in different combinations, you're still using the same pieces in a lot of them. And trying to make things totally independent is quite difficult. So I think astronomers have a lot of work to do, but so does a lot of other people.
Right. Okay. And the last question, perhaps, by Antonio Nero Romano.
Oh yeah. Okay. So it says 2m++ only extends to z equals 0.067. So redshift correction can miss the presence of an inhomogeneity extended beyond 0.067. What do you have to say about this? Yeah, I am actually quite interested in this question. So one thing that we look at is we say, all right, do we see any kink in our Hubble diagram? And if you say, okay, there's just some inhomogeneity happening at some redshift, we should see it, and just things look quite flat in our Hubble diagram. Now that being said, then you can bring up anisotropy, that kind of some part of the sky that maybe there you kind of see something weird, and we kind of have to wait a bit till LSST, which will really have this kind of full sky sample to look at. So I'd say it doesn't look like there's something there, but we need a much bigger sample to really definitively answer this.
Okay, well, thanks a lot, Dan. This is very clear talk. And before we move to the next talk, I do have a smaller announcement. I mean, just Pilar Ruiz Lapuente, who is one of the convener of tomorrow White Dwarf Explosions parallel session, reminds me that some further discussion on the H-naught tension in Type 1a supernovae will also take place tomorrow afternoon during this parallel session. So with that, thanks again. We can move to the next talk by Mark Mikomsky, again on the Hubble tension. Mark, are you on? Ready?
Yes, I'm here. Can you let me start my video?
Sure.
There we go. And let me share my screen. Okay.
Good, thank you.
Let me change this for 1 second. Okay, can you see that?
Yeah.
Okay. So my talk is going
You're
to be
still not in presentation mode, though. You are in slide view mode.
I see. You prefer it the other way? Okay.
You have to play it.
Give me 1 minute here. Does that make a difference, or is that not what you want?
No, it's just frozen. Okay. Now it changes a bit, but still you can see the slides on the side.
Okay. 1 second.
I'm not good at PowerPoint, so.
Hold on. I know what to do, I think. Give me 1 second. Okay, how's that?
It's fine. It's still not presentation mode, but I think we can see the slides. I mean, perhaps you can click on the little icon to the bottom next to the volume bar. If I remember correctly.
Presentation mode in my screen.
Otherwise, I think.
I'll try one more time.
Otherwise, I think we can go ahead. Oh, no, now it's gone.
Yeah, okay.
I think we can be happy with that view. Okay, that's fine now.
Okay, sorry about that. So this talk will be related to the prior two, but will be, and also to the ones that follow, but this is going to be a theory talk as opposed to an observational experimental talk. So I don't really have much to add to what was said in the prior two talks about the experiment and observation, but I'm going to try to discuss possible theoretical explanations. So before I get going, I just want to mention the names of my collaborators. Tanvi Karwal was a graduate student at Johns Hopkins when she did this. She's now a postdoc at Penn. Vivian Poulin was a postdoc at Johns Hopkins when we did this work. He's now at Montpellier. Tristan Smith is a Swarthmore professor. He was on sabbatical at Johns Hopkins when we did this. Kim was a postdoc at Johns Hopkins. She's now moved on to UT Austin. Jose is a current postdoc. Simeon was a postdoc. It's for some of the early work, and he's now at UC Riverside. Joseph Badler and Devin Walker were involved in some of the work that this was based on back in 2014. Joseph is now in Vienna, and Devin is at Dartmouth College. So the point of this talk is to try to describe or discuss possible theoretical resolutions or physical models that could account for why the Hubble constant measured locally differs from that inferred from the cosmic microwave background. And you know, when I am told by my observational colleagues that there's a discrepancy between the supernova inferred measurements of H0 and those inferred from the CMB, there are several possible explanations. One is that there's a possible problem with local measurements. Another is that there's a problem with the CMB measurements. We've heard about both of these. There might also be a problem with both. But what I will try to focus on is new physics. So if this discrepancy survives and is real, then it implies that there's some new physics beyond that in the standard cosmological model, and that is what I will discuss. So here is a snapshot of, or sorry, a very poor artist's rendition of the universe. And the reason I'm showing this to you is because before I describe new physics models for the Hubble tension, it's important to understand how the Hubble parameter is inferred in particular from the cosmic microwave background. And the reason is that, as we've heard from George's talk, lambda CDM provides an outstanding good fit to the cosmic microwave background data, and those measurements are very sophisticated and very precise. And if we are going to try to change the standard cosmological model in order to account for this Hubble discrepancy, we need to do so in such a way that the remarkable agreement between the lambda CDM theoretical predictions and the CMB measurements is preserved. So when we look at the cosmic microwave background, we are looking at a spherical surface in the early universe, and we are seeing it as it was 380,000 years after the Big Bang. And the radius of this spherical surface is 13.8 billion light years. Roughly speaking, the age of the universe. And these squiggly lines are my attempt to draw galaxies. Now, when we look at this spherical surface in the early universe, this is a picture of what we see. We see temperature fluctuations of roughly 1 part in 100,000. So the red spots are hot spots, the blue are cold spots. And you see that there's granularity on all scales that can be observed all the way down to the distance scales that can be resolved by the Planck satellite, and also the finer angular resolutions that can be resolved by ground-based experiments like SPT and ACT. And you see that there's some regions that are, tens of degrees across that are hot, and some tens of degrees across that are small. But you see granularity on scales of sub-degree sizes. And you may notice, and maybe you won't, but I will explain it a little more in the following slides, that the typical sizes of the hotspots are roughly 1 degree. Now this map can be used to infer a value for the Hubble parameter. And I'm going to attempt now to describe how this is done in a semi-heuristic way. And I'm going to credit Vivian Poulin, my collaborator on some of this work, for providing me some slides to explain this. So we don't actually measure from the Hubble parameter from the cosmic microwave background. We infer it by modeling the observations within the context of a class of cosmological models that are based on general relativity. And the inference of the Hubble parameter comes from the measurement of 3 angular scales. The first one is a sound horizon, theta sub s. The second one is a damping scale, theta sub d. And the third is related to the epoch of matter radiation quality, theta e. And I'll describe or discuss each one of these one by one. The most important, though, is theta sub s, which I will talk about first. So first of all, when we look at this map, there's not much obvious structure, but when we take a two-dimensional Fourier transform, or actually more precisely a spherical harmonic transform, and then we plot the squares of the Fourier amplitudes as a function of the wave number. So the wave number in this case on a spherical surface is the multipole moment L, which on this plot goes from 2, the quadrupole moment, up to several thousand. And this corresponds to angular scales of roughly 90 degrees on the left to a fraction of a degree off to the right. When we take that two-dimensional Fourier transform and plot the amplitudes of the Fourier amplitudes squared, what we find are these bumps and wiggles in this temperature power spectrum. And these bumps and wiggles can be used to infer the Hubble parameter. So the first angular scale is the sound horizon. So in order to explain the sound horizon, I'm going to play a movie that I found on YouTube. And what we're going to see is the following. So the early universe is very homogeneous. It's very smooth. It consists of baryons, dark matter, neutrinos, and photons that have almost exactly the same energy density at every point in the universe. And now surmise that at some point in this otherwise homogeneous universe, there is a delta function spike of dark matter, neutrinos, baryons, and photons. So there's some region, very narrow, one point in space or one very small spherical volume in space, where initially there is an overdensity in the dark matter, baryons, photons, and neutrinos. If so, then the baryons and photons, which form a tightly coupled fluid in the early universe, are going to be have a pressure. This region is going to be over-pressurized if it's highly dense. So if it's denser, it's going to be higher pressure, and therefore the baryon-photon overdensity is going to expand as a shock wave into the expanding medium at the speed of sound, where the speed of sound is the sound speed for the baryon-photon fluid. The dark matter is self-gravitating, but it also experiences a gravitational potential that is sourced by that baryon-photon fluid, and so that you'll see the dark matter spreads out slowly. And then there's also the purple here, which are the neutrinos. The neutrinos are collisionless and move at the speed of light, so that initial overdensity, that delta function overdensity, will spread out with time. So this is what happens. So let me stop it momentarily. So here you see the baryon-photon fluid. The shock wave in the baryon-photon fluid is sending out a spherical shock wave into the surrounding medium. The dark matter is expanding, but only slowly because it is interacting with everything else only through the gravitational field of the other stuff, which is the early universe is dominated by this baryon-photon fluid. And the neutrinos are free streaming, and so they're developing these longer tails over here. And then if I continue to play this movie, until the time of decoupling, which is about that time, about 270,000 years after the Big Bang, more or less. What you see at the time of decoupling is that there are fairly sharp overdensities in the baryon-photon fluid at the surface of last scatter. So at this point, the baryons and photons decoupled, the photons free stream, and we wind up taking a snapshot of the universe. We wind up taking a snapshot of this baryon-photon fluid at this particular time. So in configuration space, if I have initial delta function over density, after 300,000 years at the time of decoupling of the CMB photons, there is a spherical overdensity, a spherical shock wave, a spherical shell surrounding this initial delta function, the point of this initial delta function. Now, when we take the Fourier transform of this initial overdensity, when we take a Fourier transform of the spherical shell, we wind up getting acoustic peaks. We wind up getting very sharp features in Fourier space, wiggles in Fourier space. And those wiggles in Fourier space come from Fourier space ringing of the spherical shells in the baryon photon spherical overdensity, the spherical shell in the baryon photon fluid. So the wave number of these acoustic peaks is proportional to the sound horizon to the -1, because it measures the distance that a sound wave could have traveled from the time of the Big Bang until decoupling at 300,000 years after the Big Bang. So the bumps and wiggles in the power spectrum are ringing in Fourier space. And I should say that, strictly speaking, we don't have a single overdensity in the early universe. In the early universe, we have some spectrum of fluctuations. However, in Fourier space, that spectrum of fluctuations preserves the Green's function. So in other words, this is the configuration space Green's function for the baryon photon fluid, and this is the Fourier space Green's function in the photon fluid. So these wiggles here come from ringing in Fourier space of the spherical shell Green's function in configuration space. So if the sound horizon is larger, that means that the multiple moments will be smaller. And if the sound horizon is larger than the, if the sound horizon is smaller, then these wiggles will shift to the right. So the locations of these peaks determine the angular scale subtended by the sound horizon at the surface of last scatter. So that's the first parameter that we can measure, theta sub s. And this is the most precisely determined parameter that can be inferred from the cosmic microwave background. It is measured to roughly 1 part in 10,000. There is then the photon diffusion length that we can infer from the cosmic microwave background. And roughly speaking, this can be explained through the following cartoon. So in my earlier picture, I showed a CMB surface of last scatter that was a line. However, strictly speaking, electrons and protons do not combine at some specific time after the Big Bang. There's actually some region of time over which electrons and protons combine. So as a result, not all CMB photons scatter precisely the same time, or last scatter precisely the same time. There's actually some spread in the scattering time. So the CMB surface of last scatter is not really a surface of last scatter, it's sort of a smeared out surface. So as a result, if there are fluctuations on scales, distance scales smaller than the thickness of the surface of last scatter, they are going to be smoothed out. So when we look in Fourier space, what that means is that smaller scale structures, higher L moments, are going to be suppressed. So this is what the CMB power spectrum will look like if recombination took place at a very precise time. But since we actually have a finite thickness for this surface of last scatter, these smaller scale fluctuations are suppressed. So by measuring the fall off of the CMB power spectrum relative to what you would expect if you had a very precise, a single delta function surface of last scatter, you can infer the second parameter, which we call theta sub d, the angular scale associated with photon diffusion. And the third parameter is a little less difficult to describe in intuitive terms, but roughly speaking, it is determines or it's related to the epoch of matter radiation equality, or the amount of dark matter relative to radiation. And the reason is that at early times there is a growth of the gravitational potential due to the growth of fluctuations in the baryon photon fluid. And the dark matter and the baryons initially fall the same way in that gravitational potential well. However, the baryon photon fluid never fully compresses to a single point because it has a pressure, and at some point that baryon photon fluid expands back. But at some point, when it becomes sufficiently underdense, it then expands, contracts again. And so the baryons and photons are oscillating with time. And there is a difference, though, between the odd-numbered peaks and the even-numbered peaks. So if for the odd numbered peaks, the baryon photon fluid is falling in the same way as the gravitational potential. And so these peaks receive a boost due to gravity. Whereas the even number peaks, the baryon photon fluid is moving away from the dark matter fluid. And so there is a gravitational suppression of those. So by measuring the amplitudes of the odd peaks relative to the even peaks, we can infer the epoch of matter radiation quality, or in other words, the matter density relative to the radiation density. So we have three parameters that we can infer from the cosmic microwave background: the sound horizon, the damping scale, and matter radiation equality. Now, these three depend in the standard cosmological model on some combination of the dark matter density, the baryon density, and the Hubble constant. So we don't really measure the Hubble constant. There's some mapping between these three phenomenological parameters and these three cosmological parameters. And if we know these three, we can infer some combination of these three. Now, it turns out, as I said, of these three angles, the sound horizon is to determine the best, 1 part 10 to the 4th. And so any change that we make to early universe or late universe physics has to be done in such a way that this sound horizon, theta sub s, is preserved. So theta sub s is the angular scale subtended by the sound horizon at the surface of last scatter. It is the distance that a sound wave travels from the Big Bang until recombination, divided by the distance to the surface of last scatter, more precisely the angular diameter distance to the surface of last scatter. So this angle that we infer from the location of the acoustic peaks in the CMB power spectrum is the sound horizon divided by the distance to the surface of last scatter. And we can write down formulas for these, and these are actually precise expressions. They're written in a way that's a little different than we usually write them in our cosmology classes, but it is actually precise. These are precise expressions. So the angular diameter distance is the speed of light divided by the Hubble parameter, h naught, times an integral from the time of recombination until now, over time, divided by the square root of the energy density of the universe as a function of time, normalized by the energy density today, and this time is normalized by the age of the universe today. And the expression for the sound horizon is similar, except that it is 1 divided by the expansion rate at recombination, and this integral goes from the Big Bang until the time of recombination, and the speed of light is replaced by the sound speed of the baryon photon fluid as a function of time. And here the time is scaled by the age of the universe of recombination, and the energy density is scaled by the energy density of the universe at recombination. So I can combine the expressions from the two previous slides algebraically. And so what we find is that the Hubble parameter that we infer from the cosmic microwave background is the Hubble parameter at recombination times this integral, this late time integral divided by this early time integral. So if we want to increase the value of the Hubble parameter inferred from the cosmic microwave background, we can either decrease the matter density at late times, or we can decrease the sound speed in the early universe, or we can increase the matter density at early times. Matter density at early times, this denominator of this denominator. So these are three possible ways to solve the Hubble tension. It turns out that decreasing the matter density at late times does not work. Those are called late time solutions. And George alluded to this before. So late time solutions involve modifying the late expansion history to increase the angular diameter distance. But this requires an energy density smaller than in the standard cosmological model relative to the matter density today. So we're not reducing the energy density of the universe, we're increasing the energy density of the universe sometime between now and recombination, assuming that the energy density of the universe today is kept constant. So this requires that the energy density be smaller than in the standard cosmological model. keeping the energy density of the universe today fixed. So this requires some novel or new type of energy density that has a negative energy density, which violates the null energy condition. If you're a general relativist, you know what the null energy condition is. If you're not a general relativist, then the null energy condition simply states that that you cannot have negative energy density matter, roughly speaking. But even if you're willing to allow for this extremely exotic theoretical possibility, and the point of this plot, which is from a paper by Poulin et al. From a few years ago, the point is to show you that if you can in fact solve the Hubble tension if you allow for negative energy density matter at intermediate redshifts. But even if you're willing to allow for this exotic theoretical possibility, as George mentioned, you cannot get these models to work for empirical reasons. And the reason is that the sound horizon is imprinted on the galaxy distribution. So that overdensity in the baryon Green's function shows up in the galaxy distribution today, since galaxies are made out of baryons in matter. And so there's actually a peak in the galaxy two-point correlation function, the Green's function for the galaxy distribution. And that provides a standard ruler that allows you to infer the Hubble constant at low redshifts. And that this also gives you a lower Hubble constant. So the late time solutions don't work, even if you're willing to allow for this very exotic theoretical physics. There are models that you can construct where you decrease the sound speed in the early universe. I had not workable here yet, but I should change this. There have been some recent papers that discuss this. I will not discuss those. The third possibility, which has received quite a bit of attention in the past several years, is called early dark energy. And the idea behind early dark energy is to increase the matter density in the early universe, the energy density in the early universe. So what we do is we suppose that the early universe expands faster somehow in the somehow. If so, there's less time for sound waves to propagate, and there is therefore a smaller sound horizon, and we infer a larger value of the Hubble parameter from the CMB. This idea was discussed originally in a paper I wrote with Tanvi Karwal several years ago. And the basic idea is shown here. Here we see the energy density of the various components of matter as a function of redshift. So the Big Bang is off to the right, the universe today is off to the left. So we've got matter, we have radiation, non-relativistic matter, the cosmological constant, and the total energy density is given in red. And we surmise that in addition to those, we have something that we call early dark energy that behaves like a cosmological constant at early times, but sometime before recombination, which is this redshift of about 1100, this vertical line here, this early dark energy density drops faster than radiation. And so what we wind up doing is increasing the total energy density by approximately 10%, slightly before recombination, but leaving the early universe expansion and the late universe expansion at the same as in the standard cosmological model. We also, in that original paper in 2016, described two possible physical models. One is a scalar field with confining potential. So the scalar field oscillates rapidly at late times, but it has a potential that looks like an axion potential, 1 minus cosine phi over f to the power n, where n is greater than 1. A second possibility is a slowly rolling scalar field with a potential that looks something like this. And this will also give you the desired behavior. The devil, though, is in the details because we have CMB power spectra that are so well measured, we can't just monkey around with the early universe physics without actually doing some work. So in a paper that was published a few years ago, Vivian Poulin, Tanvi, Tristan Smith, and I showed that you could actually get this to work. So it's a straightforward analysis, but it's complicated. And the reason is that we have to evolve the differential equations for the evolution of all the standard components of matter and the scalar field and the gravitational potentials for each spatial Fourier mode of the primordial density field. And then we have to do so for each combination of cosmological and early dark energy parameters. So the cosmological parameters are the dark matter density, barium density, etc. And the early dark energy parameters are the parameters that describe this potential or this potential. And we used a modified version of the publicly available class, and that modification is due to Poulin, Smith, Dan Grin, Tanvi, Carwalt, and I. And we happened to do it for different reasons back in 2018, but we got lucky because then we were able to use it for this particular analysis. This slide has nothing to do with the rest of the talk, but I'm going to shamelessly advertise a recent paper that is somewhat relevant. So I put a paper on arXiv 2 months ago in which I show that the infinite hierarchy, the Boltzmann hierarchy, the infinite tower of differential equations that you need to solve to count that these Boltzmann codes for primordial perturbation solve can be replaced by integral equations. And so it's the same calculation, it's a different mathematical formulation. And if you replace this infinite tower of Boltzmann equations for the photon and neutrino distributions by integral equations, you might be able to speed up these cosmological perturbation codes by something on order of magnitude. I'm not making a more precise claim because I'm not a numericist, but as this paper describes, I wrote 2 codes. I wrote a standard Boltzmann code, and then I wrote another Boltzmann code where these infinite towers of differential equations were replaced by integral equations. And I described the way to solve these integral equations. And with that simple comparison, it's conceivable, I seem to find factors of between 6 and 30 speed up in the code. So we are currently working, some of my collaborators, Jose, Luis Bernal, Ling Yuan Li, and Bei Zhao, are working on trying to get this implemented in the modification of class. So the products of these calculations are CMB temperature, polarization, power spectrum, and galaxy power spectra. And then we have to survey the cosmological early dark energy parameter space to see whether we can find models in which there is a high Hubble parameter that still fit the data well. And this is the money plot from the analysis. So this is a subset of the 9x9 cosmological parameter space volume that we looked at. So we have 6 cosmological parameters and then 3 parameters to describe the early dark energy models. So this parameter here is the fraction of the early universe energy density contributed by early dark energy. So this is a number on order 10%, this is the redshift or the inverse redshift, the scale factor at which this early dark energy peaks. So this is a number on order a few thousand to 10,000. This is the Hubble parameter, and this is the cold dark matter energy density. These small orange contours are the result of the standard lambda CDM analysis. And so you see that we recover the standard lambda CDM analysis, standard Planck value for the Hubble parameter, somewhere around 68. But you also see that when we add early dark energy, we find regions of the cosmological parameter space that become consistent with the supernova constraints. So these are 1 sigma and 2 sigma contours for the supernovae Hubble parameters. So you find that we can accommodate larger values of the Hubble parameter. Now, what this plot does not show, but I will tell you, is that it's not just enough to show that these likelihood contours expand into regions that overlap the supernovae parameters. I also need to be able to tell you that the reduced chi-squared is good. And I don't have a plot to show that, but the answer is yes. So there are regions, so the reduced chi-squared and these regions of parameter space are comparable to those for the best fit lambda CDM model. And in fact, slightly, although not statistically significantly, better. So I was actually surprised when we got these results. I did not think that we would be able to get these early dark energy models to work, but it turns out that they can be made to work. So we have an explanation for the Hubble parameter. How are we going to distinguish this from the standard cosmological model? And the answer is with new measurements that we hope to obtain over the next 5 to 10 years with CMB polarization experiments that we hope to have over the next 5 to 10 years. And again, this is a plot that I have from our Vivian, from our paper. It's hard to see. So this is the CMB polarization power spectrum. And these light error bars over here in the pinkish color are the forecasts for error bars that we expect to have from CMB-S4. These are the current data, these large error bars. And then these are the residuals of the CMB polarization power spectrum with respect to the standard cosmological model. So you see that the current data can't really constrain them, but in the future with CMB-S4, we should be able to distinguish these early dark energy models, which have these wiggles in the residuals, from the standard lambda CDM model. So I have a few slides that describe new ways forward with the new measurements of the Hubble constant. I won't say much about them because we have experts talking about them. There are gravitational lensing time delays, which are very exciting and very promising and interesting astrophysics and cosmology. There's the tip of the red giant branch, which I think is a very interesting possibility. There are MIRAs, which I don't have a slide for, which are interesting. Over the next 5 to 10 years, I'm guessing we will have precise and robust measurements of the Hubble parameter from gravitational waves. And there's also a possibility to use globular cluster ages. This is a plot from Bernal et al. I don't know for sure, but I'm surmising that Leach might describe some of these. There's been a lot of work on early dark energy models. I'm going to just want to highlight
Try to wrap up, Mark.
Sorry?
You should try to wrap up.
Yep. Okay. So there's this particular paper over here, which I want to highlight, which addresses a very interesting question. For some reason, these models to work require that the early dark energy become dynamical at about the time of matter radiation equality or at about the time the neutrinos become non-relativistic. And so this paper has tried to address that coincidence. It's interesting to speculate that if this Hubble tension survives and if early dark energy is what's going on, it implies that there are recurring periods of lambda-like behavior throughout cosmic history because we have evidence or reasons to believe that there might have been a very large cosmological constant in the early universe, i.e. inflation, and there's also a cosmological constant in the universe today. So there was a paper by Dodelson et al. And another by Kim Greist about 20 years ago that sort of foresaw this possibility. So they had a tracking oscillating energy model for dark energy in which something like this can occur. Another possibility comes from string-inspired models called string axiverse models. So in these models, there are several hundred axion fields, any of which can act as a cosmological constant at any given epoch in the history of the universe. So at each log Hubble time in these models, there's a chance that the axion field may act like dark energy. So to summarize, early dark energy, a modification to early universe dynamics, provides an arena for solutions to the Hubble tension. There are detailed models that can be constructed and shown to be consistent with current measurements, and those will be tested soon with new data, in particular CMB polarization data. And if this Hubble tension survives, and if we do infer from it that there is dark energy, it may have significant implications for the physics of dark energy and possibly for string theory or quantum gravity. Thank you very much.
Thank you, Mark. Thanks for this overview. I don't see a question on the Q&A. Are there questions? You can also use the chat if you want, but if you write down the questions, we will keep them for the roundtable discussion later on. Here we go. Is there a constraint on early dark energy from ISW? From Joe Silk.
Great on early dark energy from ISW. If you're talking about the late ISW effect, I don't think that there is. Late time solutions can be constrained by the late time ISW effect, but not the early early dark energy. There might be something from the early ISW effect, which sort of affects the rise to the first peak, and that is presumably in the analysis that we did. The second question is, how does the scalar field couple to matter? Minimally. So the answer to that is that we assumed that it was minimally, in our analysis, we assumed that it was minimally coupled to matter. But some of my collaborators are thinking now about models where the scalar field might be non-minimally coupled. But we essentially just assumed the simplest thing, which is minimal coupling. Can I elaborate on the axion possibility? So the potential, let me see if I can find it here. The potential that I showed you is not a standard axion-like potential. The standard axion-like potential is 1 minus cosine phi over f, where n is 1. And in this paper with Pradler and Walker, we surmised axion-like potentials that were 1 minus cosine phi over f to the nth power. We didn't really construct any particular field theory models for this, although we made some speculations about how that might be done. So these are not standard axion-like models. We had to introduce them for the string axiverse model so that the dark matter axions would not come to overclose the universe at late times. But the answer to the question, can you elaborate on the axion possibility, is actually no. I can't really say much more about it.
Okay, so let's have one more question. Perhaps you can go to the last one by Carlos Arguelles, just because he had another question earlier that we could not address.
Okay, may this early dark energy contribution be generalized or changed with warm dark matter instead of cold dark matter? I think so, because warm dark matter is fairly cold at the early times relevant for these modifications of physics. So I think that to the extent that that warm dark matter or mixed cold hot dark matter can be made to work in the standard cosmological model, I mean, it can be made to work with the standard Planck analysis. I'm guessing that can probably also be made to work with early dark energy, but I haven't tried and I don't know for sure.
Okay, well, thanks again, Mark. I think we need to move on. And then again, we can further discuss this in the roundtable discussion. So the next dope would be by Wendy Friedman. We invite to join the screen and share the screen.
Yeah, I don't seem to be able to share here. Co-host. Okay, start. Let's see. Okay, looks like I'm sharing, and
Sure.
thank you for the invitation to speak. And I'm going to present today what I think is increasing accuracy in measurements of the Hubble constant, focusing primarily on the local distance scale measurements of Cepheids and the tip of the red giant branch, and in particular, some recent measurements of the tip of the red giant branch for the nearby anchor galaxies that set the 0.4, measuring the Hubble constant. Now, the last couple of decades have seen a remarkable improvement in the accuracy with which we can measure relative distances to galaxies. And I think where the focus will be in the next few years is getting the absolute calibration and being certain that we have systematics under control. And I think the history of measurements of the Hubble constant has been, over the last several decades, has been a march forward in terms of the precision that we can achieve and the accuracy. And can we improve the accuracy to the extent that if there is additional physics beyond the standard lambda CDM model, that this kind of extraordinary claim, as Carl Sagan would say, it does require extraordinary evidence. And what I'll say today is, based on recent measurements, I think we're seeing consistency with lambda CDM, in particular with measurements of the tip of the red giant branch. And a couple of years ago, our group published a paper in which we calibrated the tip of the red giant branch and extending out using type 1a supernovae, and measured a value of the Hubble constant just under 70. And in the last couple of years, we've done a number of checks of that 0 point, which I'll present today, which gives me increasing confidence that the result is holding up, and I think provides consistent check and consistency with the lambda CDM model. Now, oh, that's interesting. It's here. So if we look at our cosmology 50 years ago, in the 1970s, we knew that the universe began with a big bang, but at that time we were arguing about the value of the Hubble constant in the range of 50 to 100, a really unsatisfactory factor of 2 discrepancy. I think no one was seriously taking a cosmological constant into account, and we were considering either an open universe or a critical matter density universe, but not a lambda. And 50 years later, we've expanded with evidence of an inflationary Big Bang universe. The range in the Hubble constant values that we're now discussing has shrunk very considerably. And we're looking at a universe that is 1/3 matter, most of which is in a dark matter component, and 2/3 of which we think is in a form of dark energy. But this dramatic improvement and shrinkage of the range and values of the Hubble constant that we're talking about, I think is, we haven't taken stock of this and how much improvement there's been in the ability to measure distances to galaxies and to control the systematics. And the question before us is, are the systematics now reduced to the level that we can compare with measurements of the fluctuations in the microwave background? Now, here I'm just showing the longer time baseline of measurements of the Hubble constant as a function of time. And of course, we know Hubble obtained a value of about 500. That was revised by Walter Baade in the 1950s with the recognition that there were actually 2 different populations of Cepheids, and then settled into this factor of 2 discrepancy, which was eventually resolved when we were able to get above the Earth's atmosphere with Hubble and measure the Cepheid distances to a number of nearby galaxies. And now showing more recent data, beginning on the left here with measurements from the Key project, where we measured the distances in total to a couple of dozen nearby galaxies for which we could determine Cepheid distances and tie into a number of relative distance indicators, including type 1a supernovae. And you can see, and George showed a version of this plot earlier, that the Cepheids, as a function of time here and publication, have remained fairly steady in the low to mid 70s. What has improved are the measurements uncertainties. Those have come down with time. And the black points here are indicating the earlier measurements from the microwave background anisotropies, culminating here with the results from Planck, which George discussed. And here's a recent ACT plus W map measurement. Now, over time, of course, the values have continued to converge since the time of the Key project. The red points here indicating measurements with the tip of the red giant branch that I'll discuss in more detail, along with the Cepheids. But the tip of the red giant branch measurements are not discrepant with what is coming from measurements of the microwave background, and they're also not highly discrepant with the Cepheids themselves. Now, if we just compare the measurements coming from the CMB with the tip of the red giant branch, so I'm showing here the relative probability density distributions of both, then there is no tension. It's a 1.3 sigma tension. It's not statistically significant. And this is the result that came from our group in 2019 and a paper that I just posted to the archive last week that updates the calibration based on work by a number of people in our group over the last couple of years in checking the 0 point that came from our 2019 paper. The 2019 paper was based on the distance to the Large Magellanic Cloud alone, and we now have 4 independent calibrations of the tip of the red giant branch. So if I were to characterize the status this year, I would say, as I have alluded to, the measurements of distances have continued to improve over time. The values of H0 have continued to converge with time. And whether you infer the value of the Hubble constant from CMB fluctuation measurements or from distances in the early universe, the full range now that we're talking about is something like 67 to 73, and that's a full range of 8%. So again, considering the factor of 2, that's an enormous improvement. What I'd like to show you is that the tip of the red giant branch method is based on very simple nuclear physics. They're a lot less complex objects than the Cepheids, and I think this makes them less susceptible to systematic uncertainty. And as I alluded to in the title, I think these results are consistent with the standard lambda CDM model. You don't need to invoke other early universe physics. Now, why is the tension interesting? Why are we spending so much time discussing it? Of course, the standard lambda CDM model has been remarkably successful, as we've heard this morning, and in other contexts. But of course, we have no physical understanding of the components of this model, what the dark matter is, what the dark energy, the fundamental physics underlying the dark energy. We don't know what the inflaton is. And so it's vital that we continue to undertake tests of the standard model and these kinds of cracks that could be hinting at new physics. And I think all of us would agree it'd be terrific to find new physics. And as George presented, the value of the Hubble constant that you infer if you adopt the standard lambda CDM model that is this exquisite fit to the temperature fluctuations and now polarization measurements gives you a value of the Hubble constant to better than 1% accuracy. So that sets the bar for measurements locally very, very high. So let me turn to the Cepheids, which really have been for over a century since Hubble, the gold standard in measuring distances to nearby galaxies. It's what we used for the Hubble Key project. Hubble allowed us to get above the atmosphere for the first time. And what really changed in that epoch was that we were able to obtain CCD photometry and then ultimately infrared photometry that allowed us to correct for systematic effects such as the dust in nearby galaxies that are affecting the Cepheid luminosities, allowed us to both test for metallicity and make corrections for the metallicity, differences in the abundance, that is, of Cepheids in different environments. But getting above the atmosphere allowed us to increase the resolution and therefore get more accurate photometry to survey a larger volume, which allowed us to calibrate, for example, the type 1a supernovae. And before Hubble, there were no galaxies that were close enough for which you could measure both Cepheids and supernovae. This is the final result that came out of the Key project. This is just the classic velocity as a function of distance version of the Hubble diagram. And we used 5 independent methods for measuring relative distances to galaxies, all of these now calibrated with the HST Cepheid measurements. And showing here are the residuals. Of course, the scatter locally is much larger because of individual peculiar velocities. Those are typically 250 to perhaps 300 kilometers per second. And so nearby, this black line here is a vertical line showing the velocity of 5,000 kilometers per second. And these velocity perturbations can be a significant fraction then of the expansion velocity at these nearby distances. So you can see why ultimately we began to focus our attention on the type 1a supernovae. The samples, of course, as Dan showed beautifully, Pantheon sample there and the Carnegie Supernova Project sample, for example, many more objects that have been observed since the time of the Key project. And what is held up is the dispersion of the type 1a supernovae remains small, and these extend out the farthest of any of the other secondary methods. So I think it's important just to show at the moment when we talk about other distance indicators. So here's the distance limit of the masers at the moment. They go out to about 130 megaparsecs. There are only 6 maser galaxies in the entire sample, so they don't rival in terms of statistical precision what you can do with the supernovae. Here's the limit from surface brightness fluctuations. If you use surface brightness fluctuations, as in Blakesley et al., they go out to about 100 megaparsecs. And the gravitational wave, the single object, the gravitational wave siren 170817 object is at 40 megaparsecs. So in the realm of distance where peculiar motions are a significant fraction, again, of the expansion velocity. And we need to keep this in mind as we're comparing the values of the Hubble constant obtained from different techniques. They're both statistical and systematic issues that we need to keep in mind. And this is the relative probability density distribution, again, for the different methods that we used in the Key project. And we obtained a value of 72 with the statistical and systematic uncertainty shown here. The largest components of the systematic error bar in the Key project result were due to the abundance effect, effective metallicity, as well as the calibration, the distance to the Large Magellanic Cloud. There's been considerable improvement to the distance to the Large Magellanic Cloud in the intervening time. We're still, I think, at the point where metallicity remains an issue. But this is the overall result from the Key project. And since that time, we were able to use Spitzer, and the mid-infrared allowed us to get a longer wavelength baseline to improve our measurements of reddening for the very nearest galaxies, and in particular, improve the calibration to the Large Magellanic Cloud. And the calibration, this is a paper from 2012 based on the Spitzer data, and a calibration based on HST parallaxes, so for the first time, accurate parallaxes for Cepheids in the Milky Way, which the sample, small sample, 10 objects shown here on the left. This is a period luminosity relation, or Leavitt law in the mid-infrared, 3.6 microns as a function of log of period. And you can see that the scatter in the relation, and the points on the right here are data, Spitzer data for the Cepheids in the Large Magellanic Cloud. Scatter amounts to only 1/10 of a magnitude. That's 5% in distance for a single Cepheid. So when you have a sample of 100, then at least your statistical precision, you're getting of order of percent. And the distance to the Large Magellanic Cloud that we obtained, roughly 50 kiloparsecs, agreed well with what we had for the calibration of the Key project at the time, and led to a higher value of the Hubble constant. The value of the distance to the Large Magellanic Cloud agrees to better than 1% with the new geometric estimate of the distance to the Large Magellanic Cloud based on detached eclipsing binaries. We heard a little bit about that from Dan earlier. So the calibration now in terms of the distance to the LMC, the distance to the LMC is at the percent level in terms of recent measurements. Also, recent progress on the Cepheids, of course, is the project that Shoes undertook, which was to increase the numbers of galaxies having Cepheid measurements that also had type 1a supernova host measurements. And you can see at the bottom, the nearby galaxies, here again, M31, and the Milky Way, M31, and the Large Magellanic Cloud, relatively small scatters, agreement with what I showed you earlier. But the scatter does go up as you go to larger distances, as you would expect. The precision of the measurements goes down as the signal to noise goes down, and also as the the difficulty of making measurements of individual stars against the background light and the fluctuations in the background light of the galaxy increase with distance. And so here's the Maser galaxy. We've had some discussion of NGC 4258 here on the left, bottom left. Scatter goes up to almost 4/10 of a magnitude that you can compare to the scatter in the LMC I showed you was 1/10 of a magnitude. M101 at 7 megaparsecs, again, very large scatter. And so these get increasingly difficult with distance. Now, and the hope is to take those out to 40 megaparsecs, which is yet an even greater challenge. So in terms of the next level of accuracy that we need in measurements of Cepheids, the Cepheid period luminosity color metallicity relation, what we refer to now as the Leavitt law. The luminosity of a Cepheid is a function of the period of the star. It's a log-log relation, a magnitude, log of luminosity, and the period of the star. There's a color term. It's actually indicative of a period luminosity temperature relation, intrinsic relation for the Cepheids themselves. There's real intrinsic scatter to the period luminosity relation. And another term which allows for the luminosity of the Cepheid to reflect the abundance in the atmosphere of the Cepheid, and a term gamma that needs to be measured empirically on a 0 point. And so these many parameters in the Cepheid-Leavitt law make the 1% measurement of the Hubble constant a challenge. This is not a simple issue. And I think the important test as we go forward to ensure that we have this level of 1% accuracy is to improve the uncertainty in this gamma term, and to ensure that we have sufficient image resolution that in disentangling the effects of, for example, crowding and blending as you go out beyond 20 megaparsecs where tests of crowding have been done, and disentangling the effects of metallicity, the color term, the dust correction, and so on can be done. And I think this will come with the James Webb Space Telescope. Dan alluded to new observations that the SHOES group will get, and I'll describe later in the talk the measurements that we'll get from JWST that will allow us to improve these Cepheid measurements. Now, these are, for those of you who haven't measured Cepheid distances to galaxies, these are fields that we observe with the KEY project. These are negative images of the fields that we observed. And so the stars are dark, the dust lanes are the white patches here, and the individual Cepheids that were found in each of these galaxies are marked in each of these cases. And you can see it's not a trivial issue. These stars, Cepheids, are supergiants. They're young stars. They're located in regions in which there is a lot of dust and a concentration of star formation. The abundance will vary depending on the position in the galaxy. We know that there are abundance gradients in galaxies. The more star formation, the more processing of chemical elements. And so these images I'm showing you here, the bulk of the KEY project sample were for galaxies that were closer than 15 megaparsecs. We're now trying to push these out because supernovae are rare. And in order to calibrate the supernovae, you need to have distances increase statistically our sample size. You need to go out to farther distances. That is a challenge. So what do we need to next understand for the Cepheids? I'm showing you here data for NGC 925. It's a nearby galaxy at about 9 megaparsecs. You locate the Cepheids in the disk. Here's the projection in the HR diagram. So looking at luminosity, temperature, luminosity, color. Here are the Cepheids in the middle region here in the instability strip as the stars are evolving. During their evolution, they pass through the instability strip several times. And this is the projection that we're used to seeing in luminosity as a function of logarithm of the period. As I mentioned, the scatter is much of the scatter is intrinsic because of this temperature effect, also metallicity. But disentangling that, again, while you're correcting for these effects of dust, limited numbers of wavelengths that you have to observe remains an issue. And these are the kinds of things that as we're trying to improve the local distance measurements, we clearly need to establish that we have these kinds of effects at the 1% level. And these are models for evolution of Cepheids. We have increasing metallicity here. Whoops, excuse me. So on the left are low metallicity models, high metallicity models on the right. As you're going up in luminosity, you're looking at younger aged objects. And if you look at the evolution of stars, the red edge here of the instability strip is shown, and the blue edge depends on the ionization. The red edge depends on convection. So there, of course, understanding where exactly the instability strip resides and how it's a function of metallicity, we don't yet understand well. Different stars of different metallicities cross the instability strip in different numbers of times, and it's a function of metallicity, and the luminosity depends on the metallicity. So these are complex objects, and we need to understand better the effects on their luminosities if we're going to claim a 1% improvement. So that's why the interest in having worked on Cepheids for a very long time, we wanted to look at another method completely independent of the Cepheids to ensure that we had a way of understanding the systematics from a single method. As I mentioned in the key project, we had several different methods. And what we did was to measure the statistical uncertainties, keep those, the sample sizes of the methods that we used, so that we could have a 5% statistical uncertainty, combine the results in the end, and the overall systematics could be robustly constrained. We won't do it from the Cepheids alone. Now, the tip of the red giant branch offers a number of, I think, real advantages in terms of systematics. These stars, for those of you who aren't as familiar with them as for the Cepheid variables, these are low mass stars. They have masses about solar mass or slightly smaller. And the stars have exhausted the hydrogen in their cores. They have a hydrogen burning shell, and the temperature in the helium core is insufficient to ignite the triple alpha process, to have core helium burning. And so the burning is taking place, luminosity is powered by hydrogen burning in this shell. The hydrogen is converted to helium, is increasing the mass of the core. The temperature is rising as the star is ascending the red giant branch after it leaves the main sequence. And when the temperature reaches about 100 million degrees, and the mass of the core at that point is just under half a solar mass, the helium can be ignited, the triple alpha process begins. There's a thermal runaway because of the degeneracy, the star can expand, the temperature increases, and essentially the star rearranges its structure and ends up on the horizontal branch. But because this happens at an almost constant core mass, the ignition then occurs at a predictable luminosity, which makes it a very good standard candle. This actually is a standard candle as opposed to a standardizable standard candle in the way we think of Cepheids or supernovae. In terms of observing the tip of the red giant branch, and what this means in a practical sense is if, for example, we go out into the halos of galaxies where we measure the stars here, I've denoted the red giant branch, stars are ascending the red giant branch here. When they reach this core helium, the flash position, then they end up on the horizontal branch. So there's a very sharp demarcation, and we don't see stars, red giant branch stars, above this core helium flash luminosity. So in a practical sense, we measure the luminosity function shown here in gray and measure the first derivative of this luminosity function. We use a standard edge detection technique. And where this very sharp demarcation occurs, we measure a peak in this filter that allows us to determine this luminosity very accurately. And in practice, we do artificial star tests and inject stars for which we know the magnitudes, pull them out, and determine how well we can measure this tip. And it turns out to be very robust and very repeatable. In terms of metallicity effects, in the case of red giant branch stars, I'm showing here a sample of clusters, globular clusters in the Milky Way, here low metallicity clusters. So here you can see the giant branch and the horizontal branch again, and a sample of higher metallicity clusters. These clusters now have metallicities that can be measured spectroscopically. I'm just showing extraction of some spectra here. This is the magnesium index here, but you can see by eye relative to the high metallicity clusters, the spectroscopic abundances are well measured, and the colors or the temperatures in the Hertzsprung-Russell diagram. And so this is the I band magnitude as a function of the V minus I color. The lower metallicity clusters have bluer giants than the redder clusters. So there is a difference due to metallicity, and empirically we can determine that even without individual spectra. But the point I want to make is, unlike the Cepheids, where we don't know the metallicities of the individual stars, in fact, we use oxygen to hydrogen in H2 regions as a proxy for the Cepheid metallicities. The color magnitude diagrams themselves tell us the metallicity of the objects that we're observing. And in the I band, the magnitude of this helium flash luminosity is remarkably stable. As a function of metallicity, it's a very small effect, but we can calibrate it directly empirically, which we can't do for the Cepheids. In terms of location of the tip of the red giant branch stars, here is these are a field in the Cepheid field in NGC 4258, the Maser galaxy that we talked about. Again, we're confined to the disk with Cepheids because that's where the young stars are found. What we do in the case of the red giant branch stars is go out along the minor axis of these galaxies into the halo, shown at the same contrast. The background contamination from the disk is, of course, reduced as we go out into the halo of the galaxy. So the photometry is much easier, it's more accurate. The reddening is almost negligible in the halos compared to the disks. The metallicity we can determine directly, and it's small, but we can empirically measure it. And so this is this Advanced Camera for Survey ACS field of NGC 4258. This is now the giant branch that we measure. Here is the peak in the filter that delineates the position of the core helium flash. And the work that we did in our 2019 paper, here are the HST fields that we observed, again, along the minor axis of these galaxies. So staying away from the disk, but looking at the halo populations of the red giants. And there are 18 in that publication calibrators, which is very consistent with what now is available for Cepheids. There are 19 published calibrators. We have one additional one since that time of the publication of the 2019 paper. And here is one example. This is at 11 megaparsecs, the galaxy Messier 66. We ignore the inner part closest to the disk, measure out in the halo, so you can see these stars are well separated. Doing photometry of these stars is very simple. We don't have to worry a lot about overlapping crowded images in the way we have to worry about when we do Cepheids. This is a comparison now of published tip of the red giant branch and Cepheid distances. Here are the residuals, and the red points are for galaxies that have all three, tip of the red giant branch, Cepheid, and supernova distances measured for them. This is a blow up of the red points, and you can see that the scatter is larger than the quoted uncertainties, and there is an offset of about 0.06 magnitudes. Now, some hint of where some of the difficulty may be, this is now the supernova luminosity. So these are the same supernova luminosities. This is the sample of overlap between Cepheids and tip of the red giant branch and supernovae. But the dispersion in the TRGB calibrated supernova magnitudes is comparable to what we get for the supernovae, about 1/10 of a magnitude. It's larger for the Cepheids, same galaxies. So We don't yet understand the reason for that, but another indication that perhaps there are some systematics in Cepheids. There's been some independent measurements of the tip of the red giant branch distances. Dan mentioned the galaxy for which a Cepheid galaxy has been measured independently. There are 10 galaxies here that group with Brent Tully has measured using completely different software to measure the luminosities, to measure the tip of the red giant branch, to do the edge detection, and so on. These now have all been zeroed to the maser distance of 4258. So we're comparing the relative distances here, and you can see that the overall agreement is at the 0.5% level between the two distance scales when you use the same calibration. This is the same group. If you calibrate with respect to the Cepheids, use the 0 point from the Cepheids, then and calibrate the Tully-Fisher relation, then you get a value of 76. If you use 4258, then you get a lower value of the Hubble constant. But the important thing is that these are one-to-one measurements. Again, so not many distance indicators have the opportunity where you can compare on a galaxy by galaxy basis how well are the relative distances being measured. I'll go quickly through the supernovae. The supernovae that we use to determine the Hubble constant based on the Carnegie Supernova Project. This is a project carried out at Las Campanas. Mark Phillips and I were co-PIs on this program. Was set up to deal with systematics, to get multi-wavelength photometry, 10 different filters, also spectra that or time a cadence to allow us to measure these over time, get K corrections very accurately. It's a self-consistent data set, and it was designed for dealing with systematics. This is a plot from our 2019 paper, the Hubble diagram. The TRGB calibrators are shown here in red, and the Carnegie supernova data shown in blue. And here is the value of the Hubble constant that we get, slightly refined in a later paper in 2020 that spelled out how we use the Large Magellanic Cloud as the anchor galaxy for this calibration. So at the time of this early result, we had only the one measurement to the LMC, and in the subsequent time, we have now measured TRGB distances and calibrations to globular clusters in the Milky Way, to NGC 4258, the Maser galaxy, and also to the Small Magellanic Cloud. So let me show you some of the new data. This is work that was led by a student, Will Cerny. These are
wrap up, Wendy, if you can. You should try to wrap up if you can. Yeah. Okay. Thank you.
And so these are clusters with a wide range of metallicities. We have calibrated to the horizontal branch, so this nothing to do with the tip of the red giant branch. We then measure the position of the tip of the red giant branch, having calibrated to the horizontal branches, and we end up with a calibration that agrees to 1% with what we published for the LMC. We also have measured the Maser galaxy, NGC 4258, again, out in the halo of the galaxy. There are measurements that have been done in the disk, but for all the reasons I've elucidated, you don't want to make these measurements in the disk where the crowding is worse and where the dust is worse. Again, we find agreement at the 1% level with the value that we obtained from the LMC early on. Taylor Hoyt, a student at Chicago, has been measuring many fields, thousands of stars in both the LMC and the SMC. You can see the well-determined peak of the luminosity function again for both of these galaxies. I refer you to a paper he just posted on the archive last week, where he goes into great detail of how to make these measurements. And again, very good agreement in all of these anchors. I won't say much about Gaia simply because at the moment there is, I think most of the people in the Gaia collaboration agree that there's a minimum systematic error floor. These are measurements of the variations in the 0 point with respect to both background quasars and also here with respect to the Large Magellanic Cloud, which limits the uncertainty, the accuracy with which you can determine the calibration for the Milky Way, either for Cepheids or for the tip of the red giant branch. So we will hold out for DR4, the data release 4. This is just showing you the position of the tip based on our calibration. You can see it's not a very good fit if you have a value of the Hubble constant of 74. And here are the limits showing the improvement when we were arguing about 50 to 100. Astrophysical distance indicators now have considerably better accuracy than they did at that time. And I think with the calibration coming eventually from Gaia DR4, this will be strengthened considerably. I just want to amplify on something that George said. The bottom here is a comparison of the tip of the red giant branch Hubble constant compared to the Cepheids, and you can see that there is a bit reasonably well. So when George earlier compared the tip of the red giant branch and the Cepheids here now calibrated with the LMC, the agreement, in the anchors, the agreement is not very satisfying. If you look at the Milky Way, again, the earlier calibration based on scanning parallaxes gave a large value of the Hubble constant for the Milky Way, something like 76. That's been revised now with this Gaia 0 point that is, I think people arguing about whether the uncertainty is 1% or 5%. The Shoes team argues that it's 1%, and that gives it considerable weight. But I think the Gaia team and other groups that have looked at this I think this is still a topic of a lot of discussion. How well are the Milky Way Cepheid parallaxes now constrained? And so the anchors, of course, set the whole 0 point. If the distances to the anchors change, the overall value of the Hubble constant changes. And there are very few anchors. So in common, we have the LMC 4258 and the Milky Way. So I think this is an area where, as George has pointed out, there is local disagreement. And the point that I want to make is that the distances to galaxies, there's one distance to each galaxy. And so if there's a discrepancy in our distances, this is not indicating early universe physics. We have to get to the bottom of these discrepancies, I think, before we can confirm that there is additional physics beyond lambda CDM. This is my version of the plot that we see a lot of. Dan showed where a plot of the Hubble constant that shows Planck on the left, and then all of the calibrators, all of the distance measurements that give high values of the Hubble constant. I think what we need to keep in mind are the uncertainties. These are the relative probability densities for each of the methods that are listed here with the quoted uncertainties from each of these papers. And at the moment, both statistically and in terms of systematics, the two distance indicators that I think have been studied in the most detail where we can make one-to-one comparisons are the tip of the red giant branch and the Cepheids. And I would, let me just say, I think the way forward is to use JWST. We've got a program that will allow us to make measurements of Cepheids and the TRGB, as well as carbon stars as an independent third check. So we will get to the bottom of these issues. And I'll just conclude by saying that I think at the moment we have a number of high accuracy and physically based methods that result in values of the Hubble constant between 67 and 70, and comes from CMB, temperature and polarization, BAO, and the tip of the red giant branch. And the evidence for new physics is coming from the Cepheids and other methods calibrated by the Cepheids. We need to be cognizant that there are systematic errors in the local distance scale at the 2 to 3% level. So the Hubble tension, I'll say, remains unresolved, but discriminating amongst the various issues and finding a way beyond these discrepancies, I think, is going to happen in the short term. There are lots on the horizon that will allow us to address these issues. So I'll stop here. Thanks.
Okay, thanks a lot, Wendy, for this comprehensive review. I'm afraid we are running late, so I wrote down the questions there on the Q&A right now, so we'll try to address those. At least I'll ask Wendy whether she can kind of address those in the roundtable, and I will ask Priya to come online. Okay, so this now will move past, I mean, at least beyond a bit H0 tension. And Priya, go ahead. Is density lambda CDM on small scales with cluster lenses? Thank you for joining.
First, I wanted to thank the organizers of the Marcel Grossman meeting to give me this opportunity to share some exciting new results. And and I think what is intriguing is the new sorts of tensions that are appearing in the standard cold dark matter paradigm. We've heard several talks now about the global properties and in particular the expansion history of the universe. So what I'm going to be presenting to you here is an intriguing result of a mismatch between theoretical predictions of our standard cold dark matter paradigm and observations, in particular lensing observations from cluster scales. And first I wanted to thank my collaborators, and in particular I want to give a shout out to Massimo Meneghetti and collaborators in Europe, including our session chair, without whose observational follow-up work, much of what I'm going to present today with regards to this intriguing mismatch and gap between theory and observations would not have been possible. And I also want to give a special thanks to my long-term collaborators as part of the CATS team, with whose help we've been constructing very high resolution mass models for lensing clusters using Hubble Space Telescope data. So as you all know, from our most recent and updated inventory of the universe, we know that the bulk of the components of the universe, the main constituents, dark matter and dark energy, have been really elusive in terms of their overall nature. However, one of the real successes with the cold dark matter paradigm has been the prediction of the properties, the gravitational properties of cold dark matter, and the various scales on which these predictions have been ratified. But with the growing higher resolution observations across wavelengths, we've been able to now start stress testing this model on small scales. And I want to start off with just motivating that, there has been evidence on a range of scales from epochs, cosmic epochs, for collisionless dark matter. So the standard cold dark matter paradigm has been quite resilient and has been quite robust, although there have been tensions and mismatches and deviations from predictions that have been reported from time to time. And one of the key things about the paradigm is that the properties of dark matter, the clustering properties of the dark matter, the interplay with baryons that has been predicted so far, have worked remarkably well on fairly large scales, on galaxy scales and group scales, as well as cluster scales. But when we then hone in on smaller scales and are able to do much more detailed comparisons because of the availability of both high resolution observational data and high resolution simulations, much more sophisticated cosmological simulations. So within the context of the CDM paradigm, although we know that the universe is dominated by dark matter, once again, we do not know the precise nature of dark matter, and the particle nature of dark matter remains unresolved in terms of the masses of the particles, or their possible weak interactions, self-interactions, or weak interactions. However, the range of masses that has been proposed spans a huge set of and orders of magnitude, starting from the very popular weakly interacting massive particles, sort of WIMPs in sort of the GeV range, to very, very light particles, axion-like particles, very low masses, to all the way to primordial black holes as potential dark matter candidates as well. So there's been a real range in mass, and while observational data from astronomical observations cannot pinpoint the particular particle nature of the particle, because we have access only to aggregate properties and aggregate behavior of cold dark matter particles. So there have been very concrete predictions, and in particular, some of the predictions that I'll be focusing on today have to do with the abundance, the prediction of the abundance of dark matter halos that serve as the incubators for the formation of galaxies, the internal structure of these halos, including density profiles on very small scales, and the concentration, the shape of these profiles, the concentration of matter in these individual dark matter halos as a function of scale. So cosmological simulations within the standard paradigm reported that there was a near universal shape for how cold dark matter settles down over time into virialized halos, and that is the Navarro-Franken-White profile, with clear-cut predictions for what the inner density slope, the outer density slope should be, and what the concentration ought to be. However, despite these robust predictions, and as I said, broad agreement on a range of scales, there has been trouble reported when we have interrogated the cold dark matter model on small scales. So for instance, the first signs of trouble that were reported were from studies of the internal structure of halos, the so-called cusp core problem. So it emerges that on sub-kiloparsec scales, where the resolution of simulations is particularly limited, the central regions of galaxies are also complicated by the stellar component, star formation activity, black hole activity in terms of feedback, and so on. It was found that in particular for low surface brightness and dwarf galaxies, low luminosity galaxies, that there was a departure from the predicted power law slope in the inner regions, and the density profile appeared to turn over, suggesting the presence of a constant density region in the center. So this was reported in the 90s, and however, with new improvements, both in simulations, higher resolution simulations, as well as more careful measurements of the inner density slopes of galaxies, it is now found that the inclusion of proper feedback processes that couple the dark matter and baryons in the centers of galaxies, that this is mostly resolved. So this tension was mostly resolved when baryonic processes were better modeled and included in the simulations. So this had to do with the internal structure of halos. So there was a mismatch that was reported on very small scales in the internal structure of dark matter halos. The other kind of trouble that was reported was that had to do now with the abundance of subhalos. And this is often referred to as the missing satellite problem. So when one counts up the number of satellites for a galaxy like the Milky Way, it is found that simulations predict a much larger number of satellites to have survived for Milky Way scale halos than are actually detected. And so this once again got resolved in this event. This tension got resolved when this abundance mismatch was fixed when fainter satellites were detected observationally. So advances in observational methodologies, the ability to detect lower surface brightness objects in the halo of the Milky Way, turned up many, many more satellites So this brought the predictions of the simulations in better line with what is observed. So these two tensions that related to the internal structure of halos and the abundance of subhalos seem to have gotten resolved. And this is on galaxy and group scales. So the internal structure that we saw was a mismatch on galaxy scales in CDM, and this was a mismatch reported on group scale, so in the local group. So now what I want to show you is that with the availability of higher resolution data and sophisticated simulations, we can now probe both the internal structure of subhalos and the abundance of subhalos in another cosmic context, in the context of galaxy clusters. So this is a Hubble Space Telescope image of one of the most dramatic lensing clusters, Abell 2218, that has served as the poster child for what all we could do with the data and follow-up modeling and simulations of massive clusters that are extremely efficient light deflectors. To give you just a quick preview of what typically are the properties of clusters that are going to be relevant for the work that I'm going to talk about and their use as cosmological lenses, the composition of clusters, they are dominated, they are the objects that are most dominated by dark matter in the universe in terms of proportion of their mass. Their masses range from about 10 to the 14.5 to 10 to the 15 solar masses. They are the most massive objects in the universe, most recently assembled. 1% of the mass roughly is in galaxies, in the stars in the galaxies. 10% is in X-ray emitting hot gas, and the rest is pretty much all dark matter. So there have been many open questions for clusters that have been addressed very successfully over the last 2 decades that have to do with the overall mass distribution, how well light and mass trace each other on these very large scales. But the questions that have yielded some of the most exciting answers have been the spatial distribution, the ability to map the detailed spatial distribution, the granularity of dark matter on very, very small scales inside clusters. And so there have been many techniques, but the most significant and powerful technique has been gravitational lensing. And so here I just have a quick schematic showing you how the deflection of light from background galaxies deflected by the presence of a massive foreground cluster lens provide you access to the details of the mass distribution of the cluster lens. So with the strength of lensing, the light deflection depends both on the underlying cosmological sort of geometry, as well as via the distance ratios. And it also depends in detail on the mass distribution of the lens. So it's all the mass integrated along the line of sight in a cylinder from us to the sources. And so since the cluster is the dominant mass distribution in the cylinder, the high quality of data allows us to map the mass distribution in the cluster lens in exquisite detail. And so this is something that has been pursued for the last 2 decades, facilitated by the extremely high resolution data from the Hubble Space Telescope that has transformed this field. And so now we are able to not only detect the most dramatic lensing features, which are the highly distorted arcs and arclets, but also detect very, very small scale lensing effects that are produced directly by the further granularity in the mass distribution in clusters of galaxies. And so lensing has been observed and exploited on a range of scales. So I'm just showing you a gallery of galaxy scale lenses as well. So both cluster and galaxy scale lenses have really transformed our understanding of the detailed distribution of dark matter. So the power of substructure, this mapping small scale structures using lensing, has been that cold dark matter provides a very concrete prediction for the mass function of substructure on smaller scales. And so, for example, we have that the number of subhalos as a function of mass scales as mass to the -1/8. So this very concrete testable prediction as a function of scale has been used both on cluster scales as well as galaxy scales. And the reason this is important is because this subhalo mass function is a very strong reflection of the underlying nature of dark matter. So in this little animation, I'm showing you slices from two simulations, one with cold dark matter and the other, the smoother version with warm dark matter scenario. So where the nature of the dark matter particle reflects directly in terms of the abundance of substructure that you see. So what you see here, even by eye, is that the warm dark matter simulation predicts a lot less substructure than the cold dark matter one. So if we are able to map substructure, count up the subhalos, so do an abundance estimate, we can test cold dark matter very, very to high degree of precision. Of course, the rub here is how well can we construct these mass models to derive the subhalo mass function, and what is the mass range over which we have access to the mass function. So in order to do that, we need really exquisite data, as I've mentioned multiple times. And in particular, when we are able to exploit lensing effects on a range of scales. So we exploit the strong lensing effects that have to do with sort of the isotropic magnification region of the cluster, where the mass, surface mass density is in excess of a critical value for the given configuration. And so the effects that you see manifested in this regime are multiple images, highly distorted and magnified arcs. And so we combine the effects that are seen, observational effects seen in the strong lensing regime with the weak lensing regime, where what you really see are not such dramatic effects, but slight changes in shapes, a coherent change in the shapes of background sources. The distant background galaxies whose light is deflected are seen as slightly elongated. And so these two regimes in the mapping are combined, and they powerfully combine to give you a detailed mass model of the cluster lens. So I wanted to pay a little bit of attention to the strong lensing regime, because this is the regime that we are going to be exploiting to test substructure on small scales. So what this shows you is, lensing is essentially a mapping between the source plane and the image plane. So what you see here is the relative configuration, the relative position of the source with respect to the detailed mass distribution in the foreground is what determines the shapes, the highly distorted geometries that you get for the strong lensing features. So you see that depending on the alignment of the source behind the cluster lens, you get a range, a plethora of shapes. And in particular, the multiplicity, multiple imaging is determined by when the source lines up just behind the caustic. So this region, this diamond-shaped region, depending on where the source lies with respect to that region, you get these multiple images, multiple magnified images for clusters. So in order to model clusters, we have come up with a framework. It's sort of an old framework that has worked incredibly well, where we partition the gravitational potential of the cluster into smooth components and a sum of perturbers. And this reflects what is predicted by cold dark matter. So it maps incredibly well to the predictions of simulations. And so this kind of mapping framework, this kind of partitioning of the mass has been fundamental in our ability to directly compare observationally determined lensing mass models with the predictions of cold dark matter simulations. So here is an example of the mass reconstruction of the cluster Abell 2218. And what you see in the right-hand panel are the small scale distributions that you see as small scale peaks. On the overall smooth, you can see by eye the from the image itself, you can actually see from the positions of the highly distorted arcs where the large scale smooth distributions of mass lie. And for the smaller scale distributions, they are visualized there to show you. However, part of this modeling framework has traditionally involved assuming a parametric model for these subhalos for these smaller scale distributions. And so they've often been assumed to have properties that a profile the pseudo-isothermal elliptical mass model typically, and key characteristics of that profile are assumed to scale with the light, the overall light. So these are relationships between the mass and light that are assumed a priori. But it turns out now that the data is so good that we can actually free ourselves from constraining those relationships and leave those indices that relate to mass to the light free. So here is the first early results. So these are old results from comparing the results of mapping the mass function of clusters with simulations from the Millennium Run. So overall, there is a reasonably good agreement. Actually, there's a remarkably good agreement if you look at the axes on these. The y-axis is actually the number of clumps. So this is the number of clumps as a function of the mass of clumps, the subhalo mass function. And there's remarkable agreement with predictions from the Millennium simulation. That is the black histogram. The data is in the red histogram. The cases where you see less spectacular agreement, like in this panel for 024, are when you have two massive subclusters that are merging, and a configuration like that did not have an equivalent in the millennial box. So in order to see how you could push this method of comparison, so I just showed you that, when you look at the abundance of subhalos within clusters, cold dark matter passes the test. So now let's push and see if we can say something about the internal structure of subhalos. Can we test that on small scales? To do that, we need extremely good data and as much data as possible. So we combined a shallow survey, data from the CLASH program, about 25 clusters, with a much deeper survey, the Hubble Frontier Fields clusters, where you had deep imaging of 6 clusters. And then we used the state-of-the-art illustrious simulations. And once again, we find that with all these updated higher resolution lensing mass models and updated simulations, the agreement in terms of the abundance of subhalos looks incredibly good. However, there's something that starts to show up with these higher resolution mass models, and that is that the radial distribution, the predictions of the radial distribution of subhalos from cold dark matter do not match the real universe. And so we found this mismatch. So we found that in the real universe, there is a concentration of subhalos in the inner regions, these subhalos that are absent in simulations. And so the first way that, the first explanation was that perhaps in simulations, you are tidally disrupting too many subhalos. They are not making it to the center. So that was one suggestion. And we wanted to look at this much more deeply. But we wanted to make sure that we had the best possible lensing mass models whose systematics we understand incredibly well. So here is a sample for ABEL 2744, one of the Hubble Frontier Fields clusters for which we have the highest resolution mass model. So we have exquisite mass modeling, but what we needed on top of that is spectroscopic data. Not only do we want spectroscopic confirmation for all the multiple images, but we also want to obtain velocity dispersion measurements, central velocity dispersion measurements for clustered galaxies. Because remember, this is a parameter that we model and combine with the light distribution in terms of scaling relations. But a direct measurement rather than a model prediction is what we were looking for. So with MUSE, with spectroscopic data from MUSE, we were able to tighten lensing mass models for a class of clusters. And so then what we need is a new metric now. So we need a new metric to understand the details of the mass distribution in the internal regions of subhalos inside clusters. So this new metric is a galaxy-galaxy strong lensing cross-section. It turns out that if dark matter is really concentrated on small scales as clumps. These clumps, individual clumps, can act as lenses upon lenses, or lenses on top of the smoother lens of the cluster itself. And so the metric that we devised is the areas of these caustics when mapped onto the source plane that are produced, a smaller scale caustics, the smaller scale diamonds that are produced by the granular dark matter on smaller scales, the subhalos. And these, we can understand the abundance and the internal structure simultaneously by looking at the area of these caustics. So if you add up the area of these caustics, then because these are what produce these smaller scale strong lensing events. So what we found is that if you compute the galaxy-galaxy strong lensing probability from observed clusters, so these were 11 clusters taken from the CLASH and the Hubble Frontier Fields program. So that is the orange line that is shown here. And then we compute the equivalent quantity in orange from simulations, and the data is shown in the blue-purple curves here. And remember, the lensing probability is a function of source redshift. So this is plotted as a function of source redshift. And what we find is there is an order of magnitude discrepancy between the predictions of the cold dark matter model. So the theoretical predictions are an order of magnitude lower than the real universe, than the measurements in the real universe. So what this suggests is the inner regions of cluster galaxies, so the subhalos, cluster galaxies, are much more concentrated. The surface mass density inside these subhalos is much larger than predicted by cold dark matter, because they produce an excess of strong lensing events on these small scales compared to the predictions of cold dark matter. So obviously the question of great interest for us is to see what might be possible reconciliations for this discrepancy. First of all, we did many tests, and the details of this can be found in a science paper that we published last year. But let me quickly tell you what are all the possible reconciliations for this discrepancy and resolutions, and what is the final analysis. So of course, there is the issue of the accuracy of lens models. And as I said, these are techniques that are well honed in terms of our understanding of the systematics. And possible contribution of line of sight substructures. We've done many tests, and because we used mu spectroscopy, we actually have effectively done a redshift survey through the cluster. So we are able to map all the structure that is pretty much along the line of sight behind the cluster. And we do not find that the contribution of the line of sight substructures, first of all, the line of sight substructures do not substantially contribute to the actual caustics, the secondary caustics that are the key metric in our observations. And then can this be a result? Can this be some kind of numerical artifact in the simulations? Could it just be the simulation resolution? It turns out that that does not seem to be the case. And as I mentioned earlier, could it just be that, in simulations, there is a more efficient disruption, artificial disruption of subhalos? They don't survive, so they don't reach the inner regions. And so it turns out that cannot account for, that can maybe at most account for a factor of 1.5 or so of this discrepancy, but not for the order of magnitude. Could there be any selection effects? No, we believe that our simulated analogs are as representative a sample as the lensing clusters are, i.e. they are the most massive clusters in the sample. Or is there anything does this tell us about limitation in the simulations with the modeling of feedback processes? That does not appear to be the case. Although what is currently underway is that we are going to be doing this, recalculating these galaxy-galaxy strong lensing probabilities using a range of independent simulations for many different groups around the world that have been doing these simulations. But our results appear to be very, very robust. And so I'll just close. This is my final slide. So there are only two possibilities that are actually left. One is that there is that we have a poor understanding of the interplay between dark matter and baryons in cluster cores, the inner regions of cluster galaxies and clusters themselves. So maybe it's a physical process that we are not adequately modeling or accurately modeling. Or, of course, the more exciting possibility has to do with the fact that this could signal, like all the other speakers have mentioned with the Hubble tension, this could actually reveal a deeper problem in the cold dark matter paradigm. And these kinds of gaps between theory and observations have been very, very important so far, because they allow you to interrogate the current paradigm, test the current paradigm, and might suggest potential refinements or revisions that might be needed, and or they might actually point the way forward to any radical revisions, for example, in the assumed nature of dark matter. So the data from upcoming space missions and simulations, JWST, Nancy Roman, Euclid, should really allow us to push much further and test and see whether this metric, and we are working on many other new metrics to stress test cold dark matter on very small scales. So let me stop here and thank you for your attention.
Thank you, Priya. So let's see, we do have time for a couple of questions. See the Q&A. Can you read? Would you mind to read?
Yeah.
Or I can do it, but the one by Daniel Gilman.
Right. So I just want to let me take Daniel's question first. Yes. And the question is that I'm looking at the more massive subhalos. Indeed, there is a selection of subhalos. First of all, we are only able to map subhalos with the best lensing data in hand at the moment that are above 10 to the 9.5 solar masses and above. We do not have the capacity at the moment to push further down in the mass function. And on top of that, in order to compute the galaxy-galaxy strong lensing cross-section, we have actually used subhalos that have an effective Einstein radius that actually ranges from about 0.5 arc seconds, but is smaller than 5 arc seconds, because we want to make sure 5 arc seconds is roughly the kind of deflection that is produced by a group of galaxies. So what we have, this calculation and this metric is very meticulous in terms of what is allowable with the current observational constraints. So for example, the 0.5 arc seconds ensures that we are able to resolve these small scale strong lensing effects that are well above the resolution limit of the Hubble Space Telescope sort of pixel size. And the further on, the question Daniel asked, can this method be competitive with stellar streams, dwarf galaxy counts? Oh, absolutely. And in fact, I would think, my instinct that this method is actually significantly more powerful, except that clusters and cluster lenses are rarer. And however, we now have close to 40 clusters with incredibly good mass models. So I think that the prospects for this method are really extremely promising. And there are scales that this method can probe that no other methods can really give us access to. The second question is from Mark, asking whether whether the simulations have the adiabatic contraction. Illustris TNG is much more contracted. Yes, no, that's a great question, and I think that we are expanding the range of simulations with which we plan to do our comparisons, and the next phase of our work will look at Illustris TNG as well as the 300 project and many other projects. Yes, this is what we plan to do next.
Okay. Great, thanks again, Priya. Of course, again, also on this, we can further discuss it in the roundtable. So I would ask then Licha, please, to come online and share the screen.
Sure. Let's see if I can operate this.
Good, thank you.
Okay, good. Can you see?
Yeah.
Start my video. Okay, I can do that. All right. So thanks to the organizer for giving me this opportunity. And what I'll also try to do is sort of to ease into the roundtable and the discussion session later on. And the title I have is the Unreasonable Effectiveness of Lambda CDM. So, well, we have this standard model of cosmology that is extremely successful. It just 6 numbers and it all hangs together. It fits observations of different epoch of the universe that relies on different observable and relies on different physics. Never mind that the model is weird, and so this must be an effective model to some extent, and therefore at some point something's got to give, and we may have to see the limitation of this model. So cosmology is special in the sense that we don't make experiment like in many other experimental sciences. We can only make observations, and with the words of Jean Peebles, we use the entire universe as a detector, but the detector is given and we can't tinker with it. So in this sense, this has driven a massive experimental effort to make the detector as big as possible, means observe as much as possible of the universe. And the Lambda CDM model has survived unscathed this avalanche of data that were driven by this motivation. And we have seen it in the cosmic microwave background. We've heard about the cosmic microwave background earlier today. The Lambda CDM model started being shaped when the data were of about this quality, and it has survived down to this much higher resolution, higher signal to noise, and even the polarization signal. And on that was on the early universe side. On the later universe side, the clustering of galaxies and larger scale structure, the state of the art when the Lambda CDM model was taking shape was the famous or infamous stickman in the CFH strip. And now the largest galaxy surveys are, BOSS, eBOSS, DES, and so on. And this little survey will like fit in a little corner down here, yet the model has survived. So there's some mixed blessing, which I call the curse and the blessing of cosmology. We can only make observation and only of the observable universe and not experiment. So we fit model that is constrained numerical value of parameters to the observation. And therefore, almost any statement is model dependent. And we always have to think when we have a statement, we say we measure this, whether it's a model dependent statement or whether we measure that quantity directly. But this is also a blessing because in principle, we can observe all there is to see. And of course, again, gastrophysics, that is nonlinearities and stuff that are difficult to model gets in the way. And this is going to be part of the name of the game. But we almost do. And this brings the idea of the ultimate survey. That is, you observe all that there is to see, and it makes no sense to repeat the experiment because you have seen everything that there is to see. And I would say that we have one of such a ultimate experiment for the primary CMB temperature fluctuation as an isotropy Planck is an ultimate experiment. I haven't said that it's for the whole CMB. There's secondary effect and there's polarization, and eventually there will be spectral distortion. But for the primary temperature fluctuation, we've seen all there is to see. And in the case of larger scale structure, there is this sort of Moore's law, and we're sort of getting there eventually with some effort. And so this has brought, this success of the Lambda CDM has brought some people to actually ask whether we live in a maximally boring universe. And I would say that boring is good. Boring is good because we can now do precision tests of fundamental physics by looking up at the sky with cosmological data, which are highly complementary to the test of physics that we can do with terrestrial and ground-based experiments. Things like nature of dark matter, dark energy, gravity, physics of the early universe, neutrino mass, and so on and so forth. So boring is good. On the other hand, there are challenges because as the statistical error shrinks, the systematic error must be kept under exquisite control. And we heard a lot of discussion this afternoon about that. And there's no systematic way to address systematic errors. And as the errors shrink, we must move well beyond spherical chaos when we model things. And so things become, when you hit the percent level, then things become incredibly complicated. But this is in the back of my mind. How do you test the model, and can you do without? Because we've seen that the model that we have, despite being so successful, must be an effective model to some extent. So at some point, something's got to give. And so if you always look at the observation with the lens of this model, maybe you miss whether the model is, completely adequate or whether there's some cracks in the model. So I like this quote by Daniel Kahneman about theories. He says that we can't live in a state of perpetual doubt, so we make up the best story possible and we live as if the story were true. And cosmology has a lot of stories. We have GR, Big Bang, choice of metric, nucleosynthesis, and so on and so forth. But it goes deeper than that. Cosmology rely heavily on model both for what we call signal and for what we call noise. Never mind that for what's noise for one experiment maybe, or for one group, it may be signal for another group. And we know that all models are wrong, but some are useful. And with 1% precision, systematic becomes the name of the game. And you have to be aware of systematic in the data, systematic in the analysis, and systematics in the model. So do we live in a maximally boring universe? Maybe so, but I think we should still keep our eyes open because there may still be surprises. And so my next question is, how would a non-boring development look like and play out? And I would like to consider, for example, something that has been discussed quite a lot this afternoon, which is the constant and non-constant. So I'm not going to say, many people ask me, do you think that the Hubble tension means that there is a problem with the model or not? And I'm not going to say that, and I don't know. But what I say is that it's a wonderful example, I think, of how a scenario may play out and how scientists will react to some sign that something may be going wrong with the model or maybe not, and what are the traps that we may fall into. So why do I like a lot what I call the H-naught game? It's because it allows us to do what I call an end-to-end test of the universe, and the error bars that we're getting are now small enough that is basically like threading a needle from the other side of the entire universe. So traditionally, to measure the Hubble constant, you build a cosmic distance ladder with, start nearby and then go farther and farther away, measuring relative distances, or redshift is easy. Measuring absolute distances is very difficult, and therefore one needs to build this ladder. The main development that happened in the past, say, 15 years or so, is that we were able to extend the ladder all the way to the early universe. And as the data set improved, this has been done again with next to percent precision, and that's where the game gets tough. And the key ingredient here has been the role played by the baryon acoustic oscillation as a standard ruler. So the idea is that physics is the sound waves in the early universe propagate until radiation and matter decouple. Mark's talk went in quite details into that. So this imprints a scale, which it's a standard ruler, which is a key observable, is useful to determine the geometry of the universe, that is expansion history, dark energy equation of state, or even an ingredient to understanding possible modification of GR. And what sets it is early universe physics, which is well known. CMB observation and early universe physics in a lambda CDM model constrain the standard ruler length to much better than 0.2% level. And that's why this has been so useful. And baryon acoustic oscillation, therefore, can be anchored in the early universe, but can be seen all the way to the very nearby and late time universe. So a glance, what has happened is that the community has been able to build two cosmic distance ladder, a direct and an inverse cosmic distance ladder. So the traditional direct cosmic distance ladder, it's to go use calibrators and then get into supernova that gets into Hubble flow. But baryon acoustic oscillation and supernovae type 1a overlap in redshift and reach a similar degree of accuracy and precision, and therefore now one can extend this direct cosmic distance ladder all the way to the early time universe, because the BAO can be calibrated to the early time physics. And the inverse cosmic distance ladder then can do the same, but the other way around. And there is no much wiggle room in the middle, even if one parameterizes the expansion history of the universe is in a phenomenological way with, say, S-spline, beams, or whatever. There's no much wiggle room. It looks a lot like lambda CDM type expansion history. The issue is that these ladders don't seem to have two anchor points that agree with each other. So we know that good ladders need two anchor points, and if they don't agree, then we have a problem. So it's important to bear in mind, again, following Mark's talk, which measurements of H0 are model dependent and which one are not, because the cosmic microwave background does not measure H0 in a model independent way within a lambda CDM, and assuming standard early time physics, then this can be done. So this is a plot similar to what Wendy has shown earlier on. And then there is the Planck CMB measurement. This is a model-dependent measurement. It's done within a lambda CDM model. There is the shoes based on Cepheid measurement here. This is the Wendy measurement, which bypasses the Cepheids. And again, these are not cosmological model dependent, this is. And then there is a measurement of baryon acoustic oscillation plus Big Bang nucleosynthesis, which does not rely on CMB data, but does rely on early time physics, and therefore does rely on a lambda CDM type framework, which lands well in agreement with the Planck CMB determination. So you can arbitrarily put a line here and say, oh, if I put a line here, these are determination that depends on the early time physics, and these are all determinations that don't depend on early time physics and only look at the late time universe. So these are early and these are late. So the first question to ask is there a problem? And how much of a problem it is both cosmological model dependent and specific determination dependent, because not all the determination, even of the low redshift or local or direct, which way we want to call it, determination of H0, are in the same tension with the early time one. Then the next question is, if there is a problem, where is the problem? So of course, the first thing one need to look at is systematics. We all have skeletons in the closet. Every experiment has skeleton in the closet. Of course, we have to look of systematics. The relatively recent development is that a lot of the data are public, and therefore independent group can look at them, reanalyze them, check them, and recheck them and compare them. And we've seen a wonderful example, for example, in the talks today, the first talk by George, and then the direct comparison that was done with some presented by Dan and presented by Wendy. So yes, there can always be systematics, but this transparency means that dumb systematics are increasingly unlikely because the community has done a scrutiny of all these results. But we should still keep looking and narrow down where the problem may be. So one working hypothesis is, well, let's say there is an early versus late split, and let's see what we can learn from that. So it transpired very early on when this sort of early versus late split seemed to appear, that one could reinterpret the H0 problem as a sound horizon problem, because if you change the calibration of the BAO standard ruler, which is this early time calibrator, then one could simply calibrate. One can agree with the local determination, because the expansion history looks a lot like a lambda CDM expansion history anyway. And so this over the year has been refined over and over, but the core of the matter hasn't changed. So then the next question is, where is the problem? Is it in any specific data set? So let's start keeping the standard lambda CDM context. So for a while, some people put the blame on Planck. But it turns out that the H0 early determination doesn't budge if one takes Planck, or now even CMB data, completely out of the window, and not only for lambda CDM standard model, but even for extended lambda CDM model, where the number of effective neutrino species or some sort of dark radiation that is there in the early universe, it's it's allowed by the fit. So before around 2019, where this plot has been taken, works that drop the Planck CMB data had to use instead WMAP and then finer scale CMB experiment like ACT and SPT. So I think I can, highlight again what George said in the first talk. It is not a fault of CMB, because we can take CMB completely out of the equation. We still need to take standard or semi-standard early time physics. Semi-standard, I say you can allow free effective number of neutrino species, and this early versus late tension, it's still there. Again, I repeat, not with all the late time determination. I'm just taking some average there. So in this paper here in 2019, in order for breaking this H0 omega matter degeneracy obtained from larger scale structure without adding the CMB, you have to have baryon acoustic oscillation at a range of redshift. And so the Lyman alpha determination was used to make this plot, but you don't have to use the Lyman alpha if you don't trust it. At some point, there was 1 point something sigma tension between the galaxy and the Lyman alpha baryon acoustic oscillation. You can use supernova instead, and you will get exactly the same answer. So. And then again, this is the more recent work by the EBOS data release 16 collaboration, but it's the same plot and the same meaning. So what is the problem? It's not in the CMB data. All early universe-based determination hover well below 70 kilometers per second per megaparsec. Many groups reanalyzed the SHUS data. Several, but not all, independent low redshift determination hovers above 70 kilometers per second per megaparsec. So it seems unlikely that the problem it's in a very specific data set, although we have heard the discussion about calibration of Cepheids, which is still open and people are, trying to sort that out. And there is a very extensive analysis presented in this paper here, where you mix and match all different type of observation and see what comes out. And I just refer to the reference here for full information. So on the data side, I predict that if this continues, maybe at some point the community may start asking for blind analysis. And I don't know if you're going to be open a can of work, a Pandora box, or whether this is, blind analyses are really good and should be done, but they are not the panacea in the sense that the blind analysis done blind for systematics. You can't blind for systematics. And they protect against the kind of unconscious observer bias. And that's not the entire problem, or not the only source of problems. So I'm just gonna drop this here and then we can discuss it later. So if the problem is not in the data, then at some point you can ask, well, maybe they have a problem in the model. So how do we go about that? And this is, heavy, and somebody did that before, and the story didn't end up quite well. So we have to be careful when we think that there may be problem in the model. So all the early time measurement assume standard or almost standard lambda CDM, and this effectively yields the length of the standard ruler, while redshift, low redshift determination do not make strong assumption about cosmology. So then you have two options. You can try to look for fix either pre or after recombination. So this plot here, it's late time determination of H, early time determination of the other anchor of this cosmic hyper-extended cosmic distance ladder. So cosmic microwave background is here, Schu's determination is here, and the expansion history of the universe constrain the product of Rs time H, and therefore it's here. The fact that these three lines don't cross is, again, the Hubble tension. So pre-recombination solution have been looked at. The problem is that you modify the model right where you most like it and where the physics is simple and is linear and is well understood. You will need to decrease the sound horizon by about 7% without breaking havoc on the damping tail and everything else, and the wonderful agreement that we've seen in the first talk of this afternoon. So this is a tall order. And it turns out that there is a narrow window to do that. And this narrow window, it's in the decade of expansion of the universe, right before recombination. And by the way, this is where the early dark energy model actually kicks in and actually modify the expansion history of the universe. Reminds me a bit of fine tuning, but you know, can also be a very predictive model if you find a model that does exactly that. So pre-recombination solution, early dark energy end up affecting the damping tail. So one can look for signature, one can try to change the initial condition, add extra component, extra interaction, energy injection, high temperature recombination, or you can even change the early time H of Z, but this will change the infer omega matter H square with scale, which is, you know, not very nice to do, but these are not all equivalent. So better data, higher resolution, a finer resolution CMB experiment with polarization will actually tell them apart. Or you can try post-recombination. You can try to think about screening, modification to GR, but my take, it's very complicated because it will have to affect several things at once. And or you can increase the freedom of H of Z. You find some the designer model, say, but the price is high. You need many extra degrees of freedom, which reminds me of epicycle, or hide it where there are no data. So that's a very tough one. And it's also very hard to change the sound horizon by 7%. You really have to tinker with things that you like and are well measured. And it's hard to just mess around with the standard ruler are seen in the BAO. You can say maybe the BAO don't see the standard ruler as the CMB puts it there, but this is extremely hard to do. And I would argue that if there is a problem with H0, then the problem will go beyond H0. So it's not just an H0 problem or a sound horizon problem. It is an omega matter problem too, and an age problem too. So if I now plot the same constraint that we've seen before, but now in an H square versus omega matter plot, the expansion history measurement of the universe, these are now relative, not absolute, so I don't have to calibrate them, just the shape of the expansion history, give me a constraint on omega matter. The cosmic microwave background, we know, give a constraint on omega matter H square, and the local measurement measure H, and therefore H square, and we are seeing the same tension again, but now we bring in omega matter. So it becomes an omega matter problem too. And then you can ask, but how old is the universe anyway? Because if you touch H0 and you keep the expansion history of the universe still lambda CDM-like, because we know it looks like, then the early determination will want a high age of the universe, while the late determination will want a low age of the universe. And this has been the work in David Valchin PhD thesis of actually going back to globular clusters and going back to the work of the 90s, but with year 2020 statistical tool and observation, and try to infer the age of the universe from the oldest globular clusters. And as I say, the lambda CDM seems to act as age, not as shoe size, although the error bars are still large, but it's nicely consistent with the cosmic microwave background determination. And this does not rely on assuming standard early time physics. It just rely on assuming a late time expansion history that looks like a lambda CDM, but then calibrating the age of the universe. So if we have to look, sorry, I couldn't resist from showing this meme. If we have to look for a cosmological model that fits the shoes, is a little bit like looking for Cinderella. And so if we look for Cinderella, we have to look for some things. The bad, W, which is equation of state of dark energy that goes below -1, or decay in dark matter. These are a little bit bad. Then there are possible ugly solutions. This may work, but they are ugly. Neutrino interaction at early time, early dark energy-ish kind of things. They work, but they're a little bit ugly. And then the good, well, the good, I guess it's for, you know, the students and postdocs that work on this and are interested. So with student now, postdoc Jose Luis Bernal, we try to put all this together in like the same plot in looking for Cinderella. And so here is the again, H naught with the age of the universe, constrained from globular cluster, shoes, Wendy's measurement, and BAO plus supernovae data. And the early dark energy model, you see that take the CMB constraints that are here and extend them down this way. But again, helps, does not, eases the tension, but does not solve the problem completely. So then let's go back in history and remind ourselves that the establishment of the lambda CDM model as we had them today passed through a plot that is called the cosmic triangle. So in there, we had an overconstrained system. The overconstrained system was omega matter plus omega lambda plus omega curvature needs to be equal to 1. And when you have an overconstrained system like that, you can always put it in a triangle plot, in a triad plot. Now, 22 years later, let's go back to the future and see whether we can come up with other overconstrained system that sort of look the same. At that point, you could measure omega k from the CMB, and then you could measure omega mater and omega lambda from one from the larger scale structure, the other one from supernovae, and that's how that cosmic triangle was being populated. And so we have already an overconstrained system that I show. One is the sound horizon and radiation drag, Hubble constant today, and then the sound horizon times h, which is what BAO plus supernova uncalibrated gives you. And then one can try to put this in a triad plot, although you have to take the log because they need to sum. You can't multiply if you want to put them in a triad plot. And so this is what it looks like. And again, the legend is like the one before. And this is just representing the same information in a different way, but I sort of hope it helps if one is looking for Cinderella to put the model prediction in something like this, and also ask yourself whether the determination is model dependent or model independent, and maybe try to come up with a big picture. But this is not the only overconstrained system you can build. The other overconstrained system you can build is age of the universe, again, Hubble constant, and Hubble constant times the age of the universe, because again, this is given by the expansion history of the universe uncalibrated in lambda CDM like expansion history at late time from, again, BAO and supernova. And then you can also show the plot like this. And again, the behavior of your proposed solution will look slightly different, because one here, for example, the age of the universe does not depend on early time physics, does not touch it's independent of what happened to early time physics. And then I also say that you can make another one, which is omega matter, which again one can get from BAO and supernova uncalibrated H, and then omega matter H square, because it's what the cosmic microwave background give you. This is the physical matter density. And I would even argue that large scale structure surveys, if they reach a big enough volume, can even give you omega matter time H, but this is, for a different story. And that's also another over constrained system, which I hope can help us sort of think about the big picture. So if we think about theoretical solution, they should not break havoc where havoc is not needed. That is, they should preserve the good agreement of lambda CDM with the data we have, and should improve and not worsen other tension. See, for example, the sigma 8. And we should quantify improvement versus predictability and degrees of freedom. So we can do a parallelism with lambda. Lambda, you just bring out lambda and then it fixes everything else that seems like the missing pieces of the puzzle. We can't just keep adding epicycle and just increase the error bars because we add parameters, reduce the tension that way. That's not satisfactory. And we should always think in the back of our mind, what is a model dependent and what is a model independent approach, and at what point we are adding epicycle. Remember, there are two different types of epicycle. There is the epicycle that were introduced in the geocentric model, and those were epicycles that were just there just to make things work, and they were not pushing you in the right direction. But there were epicycles in the Copernican model too, and the epicycle were actually useful to put you on the right track because they were telling you the orbits are not circular, they are elliptical, but you're on the right track and the sun is in the center of the solar system. So I should wrap up. So we're looking for Cinderella, what I mean there, if there is a discrepancy between model dependent and model independent determination of a quantity, and in this case, H0 is a wonderful quantity because you can see it through both sides of it, from both ends of the universe. If it's not in the data, then you ask, is it in the model? You could boost the expansion rate before recombination, that fixes the ladder, and low ratio solution have very limited wiggle room. And the trouble, if it's a trouble, it goes well beyond the H0 and distance ladder. It also involves the matter density and the age. So age determination are insensitive to things like dimming, screaming, deviation from GR on cosmological scale and distance measure. So if an I age of the universe is confirmed, model with high H0 and standard low redshift physics are disfavored. So at this point, if this happens, then I see two possible scenarios, one local and one global. The local scenario will affect H0 measurement. Only the local measurement. Could be something like a calibration, could be something astrophysical. If we want to go cosmological, it will have to be something like screening, but leaves everything else unchanged. So the actual lambda CDM, it's left unchanged. Or you have to think about a global solution, but which affects the entire history, both early and late time. But then in that case, you impact quantity well beyond H0, and it will show up one way or another. And I hope that building this cosmic triangle sort of help us figuring out whether the scenario is the first one or the second one. And I'll stop here. Thank you.
Thanks a lot, teacher, for this great perspective. And actually,
stop sharing because otherwise I can't see the questions.
Sure. Actually, just some news that Francis Halsen, who's scheduled to give the public lectures on cosmic neutrinos, has graciously agreed to postpone by half an hour his lecture so that we can finish. So I would say we'll start now the roundtable discussion, but we finish at 7:29 sharp. Okay, and I think this is our job, and then we will have the public lecture on cosmic neutrinos. Thanks again to Francis Halsen. Okay, so Licha, you can, if you want, you can take the floor, and we can make the transition. Anyone who's can obviously contribute and intervene. Where should we start? Should we start from observations or theory? I had a question, perhaps we just start. If someone had to propose an experiment, even if it's a bit challenging, but an experiment to check, the early dark energy option, what would you propose? Mark?
I think the best way to check early dark energy models is with the CMB polarization. We have a lot more information on small angular scales, and that has not yet been accessed. There are a lot of modes, a lot of information, and all of the models that we have now for early dark energy that work are by design, are designed to fit the data, the current data, but they're not pinned down by the higher angular resolution, the higher L fluctuations in the CMB polarization. So if you look at a generic early dark energy model, even one that's been tailored to agree with the current data, it tends to differ at smaller angular scales from standard lambda CDM. So I think that's the best thing that I can think of now.
But Mark, is the discrimination sharp actually between models, or is it at the edge of what will be detectable?
Well, it depends on the details of the models, but with CMB S4, it's going to be, a 3 sigma-ish. I mean, the current best fit early dark energy model that we found differs from lambda CDM with CMB S4 at the 3 sigma-ish level. I mean, the other thing is to try to identify the new physics responsible for early dark energy. I mean, usually when we talk about dark energy and cosmology, we think about cosmological experiments, but this is the vacuum that we're talking about. And, it's presumably the vacuum that we're, the Earth and atmosphere, and we are, immersed in. So, maybe someday someone will come up with a model that's sufficiently compelling and connects with standard model physics in some particular way. I would call that aspirational.
There are some questions coming on the Q&A. Some are a bit provocative, like, is cosmology science?
Well, well, I think it's a legitimate question in the sense that historians and philosophers of science have always made the case that since we can't do any controlled experiments, and the closest that we get to in terms of a controlled experiment are these numerical simulations. But I think hopefully we cosmologists and astronomers have demonstrated that we can still, test hypotheses, rule them out, validate them, and so on. We have a good record. So I think we don't have to go that fundamental in questioning what we do.
Teacher, did you have something to add at the end of your talk? Otherwise, there is a question on H0 definition. Model independent way, but.
No, I mean, I had more of a programmatic question, right. But let's take question from the public first. Okay, so H0 is by definition a parameter based on assuming the FRW. How can it be defined in a model independent way? Well, you have to assume homogeneity and isotropy, but you don't have to assume GR. That's what I mean. But you will have to assume homogeneity and isotropy. So, okay, you can do without a cosmological model as specific as, say, the full lambda CDM, but you will have to have some sort of modeling behind because you can't do control experiment, you can only do observation, but there is model dependence and model dependence.
Next question.
Oh.
Yeah, go ahead.
I'm starting to look if there are any other questions.
Yeah, there's one more.
Okay. Oh.
Understanding the
understanding age depends
Right.
on understanding stellar physics. Yes. To what extent is this needed now? What is the precision in stellar evolution model that is needed? So at the current level of error bars, that is not the limiting factor. But if we want to start shrinking the error bar considerably, then we have to start comparing different models. So this was done basically on HR diagrams of globular cluster, and therefore you need to have the tracks and you need to have the the isochrons on that. So different models seems to agree with each other well enough for the current type of error bars. But if we want to go, say, a factor of much more than a few below the current error bars, then a program needs to be done to make sure not only that the different models agree with each other, but also that all the relevant physics is in the models.
Perhaps Wendy alluded to that when talking about the TRGB standard distance candle, is the indicator. Do you think?
But I mean, isn't there also a fundamental issue with the IMF? The assumption of a near universal IMF at all epochs is kind of the basis. I mean, there is no compelling reason to discard that right now, but extremely early universe. So right now we are starting to see evidence for extremely high redshift galaxies. So there's been claims of signatures of very early galaxy formation and star formation. So the question is whether, given that the physical conditions in the universe were quite different then, could we expect the same kind of IMF? I mean, we already believe that the first generation of stars probably had a different IMF, but it's unclear that it what are the transitory states? Because a lot of this stellar evolutionary modeling rests on the premise, right, of an IMF. Right, Licia?
So for David thesis, this is insensitive to that assumption. But again, it really depends what you do with the data you have and how you interpret them. So that was checked, and it's independent on that. But other aspect may not be. So if nobody's asking any question, let me ask a sort of a programmatic question. As I think it was Wendy saying that there is discrepancy in the distance of objects, and a lot of this H0 difference in the local determination of the H0 can be concentrated or summarized in difference in determination of distance of well-defined objects. Is that correct? Am I interpreting what you said correctly? And if we can frame it in this way, then it's probably easier to have a path to actually figure out what the distance of these objects are and figure out, which is which. So is there a plan, or can you envision a plan to do that?
Yeah, there are a couple of issues. So in the 2019 paper, we pointed out that if you do, and I showed the comparison between the tip of the red giant branch and the Cepheid distances. And the first thing to be said about that is when you compare the nearest galaxies, the galaxies for which distances have been published, the agreement is very good. It's at the 1.5% to 2% level. When you go out to the distances where you then can measure supernova hosts, the agreement is not as good. And the offset is 0.06 magnitudes, what George and Dan and I were talking about. And so it's not simply a matter of saying that, oh, if you fix that the TRGB and Cepheid distances, the H knots would come into agreement.
Andy froze out.
Yeah.
It's like Dan was pointing out, or someone was pointing out with the super or the local calibration, but you don't have, and so that's one issue. Then the issue is with the anchors themselves. And in overlap, there are three. There's the Large Magellanic Cloud, there's the Maser Galaxy NGC 4258, and then there's the Milky Way. And so George's point was, if you take the same geometric distances, so we're all going by parallaxes, we're going by detached eclipsing binaries, we're going by the Maser distance, those are the same in the two. But in fact, if you calibrate individually with those three galaxies, then the Cepheids are internally inconsistent right now. And that's an issue that we need to understand. And so there are many options to explain it. One is the Gaia parallaxes right now. The uncertainties are being debated, and Dan alluded to this. The paper that he referenced by Soltis on Omega Sen is very optimistic about the uncertainties, 1% uncertainties. But in the literature, by far the overwhelming number of people who've looked at this believe it's more like 5% right now. So DR4 is going to help enormously in this. That will straighten out the issue with the parallaxes. And there's not much we can do right now because there is this variance with respect to the background quasars and smoothing the LMC and so on. And so the issue with the parallaxes right now is they're dependent on the magnitude of the star, the color of the star, and the position on the sky. So, Gaia is doing a marvelous job. It's got 1.5 billion stars and parallaxes that are more accurate than ever measured before. And so if you're interested in statistical studies in the Milky Way, it's fantastic. But getting at these issues of the calibration of H naught, where if you're going to compare with 1% or better with Planck, we are not there yet. And we'll argue until those issues have been resolved. And the other issue that George raised this morning is that if you calibrate using the Cepheids, for example, if you calibrate with respect to the Large Magellanic Cloud, the metallicity difference with NGC 4258 it's a large difference. And you get a different answer depending on what you assume for the metallicity coefficient that I was explaining. Now, with the Milky Way, the metallicity isn't an issue if you compare it with 4258, because they're both spirals, and that should not be affecting them in a relative sense. But you get it doesn't help. You get still a 3 sigma discrepancy, depending on whether you calibrate with the Milky Way or 4258. So we need to understand these differences, I would say, before we can start attributing the differences in H naught as additional physics. And so I think it is a very clear program, and it involves better parallaxes with Gaia, which will be coming, and then James Webb. And so we'll get at these issues of crowding. We'll have 4 times the resolution than now we do with HST. We'll have longer baseline to get better reddenings. Our group is going to measure metallicities directly, and we're going to have distances to the same galaxies using different techniques. So, the galaxies have one distance, right? If there's a difference, it's a systematic. It's not, it might be astrophysics, but it's not early universe physics. So yes, we need to straighten that out before we can put this problem to rest.
So I would like to just mention something which was sort of relatively new to me, but again, I may not be at the latest update on these things, which Dan seems to convincingly say that it's not a problem with the supernovae. So for some times there was an issue, say, maybe the supernovae don't behave the way we expect them to behave, and these issues with H naught rely on the supernovae. So, but then you actually say convincingly that it's not the problem with the supernovae. We should not look there.
Yeah, I mean, I would think even like a year and a half ago, there's a lot of papers coming out saying, look at supernovae, and each one of those has been addressed and kind of hasn't held water. And it's just super hard for supernovae and BAO to give low H naught and supernovae and Cepheids to give high H naught. Right. And there's still to be something wrong with supernovae. It's just tricky. So, I mean, I'm not saying supernovae are perfect. I just think it's on a smaller scale issue. I mean, George likes Pantheon plus Planck, so that's.
So I have a quick question about what
Very
it
quick,
implies
very
for
quick,
the
Priya.
local.
Just we need to finish. Very quick, very quick.
Okay, I have a quick question about whether the implications for the local volume being special. So looks like the agreement suggests that the local volume is not special then. It's quite representative.
Short answer.
Yeah, I think I think it isn't special. That's right. From what I've seen, it's whatever anyone says it is special, it's because of a lack of data in some area of the sky. But this definitely is worth looking at. I think this is still an interesting idea. Absolutely.
Okay. So really, I think we need to wrap up. I really want to thank all the speakers of this session. I think it was really outstanding session for covering such a large territory with a good blend of theoretical and observational issues. And obviously, you know, the questions will stay for a long time, and that's the fun. So I'll really thank you again, and I'll give the floor to Gregory for continuing the program. Thanks everyone, also to everyone who attended the session.
Thank you very much from our side. Thank you.
Thank you very much, Piero. Fantastic. And give us a lot of thinking, especially this last question asked by Licia. And very, very interesting, extremely. Congratulations.
Okay, thanks to you. Bye-bye.
Now we're coming to the last event of today's lecture by Professor Hudson. Francis, can you hear us?
Yes, can you hear me?
Yes, yes.
All right. Good afternoon. I'll share my screen.
Yes, thank you.
And start. It's a pleasure to have the opportunity to give this talk. And I only wish I were in Rome. Here is what I will tell you about. I'll give a short introduction to the concept of neutrino astronomy, and then how IceCube saw the first neutrinos from the cosmos, and I will update you on our latest results. This led, of course, to multi-messenger astronomy, and multi-messenger astronomy actually allowed us to see one source and maybe more, and that will be my topic at the end of the talk. So multi-messenger astronomy, of course, exists for a long time. We've seen the sky from radio to gamma rays, but you should realize that once you reach like 100 TeV, TeV is 1000 GeV, will be my unit today, then the sky turns dark. And we actually can only, if you see how deep we can look into the universe as a function of the photon energy, that's what this graph represents. Around 100 TeV, we actually only look into our own galaxy. Why is this? Well, very simple. If you have an object very far beyond our galaxy, the photons travel through the microwave background, and they will eventually interact before they reach our telescope. They will make any plus or minus pair, and if you have charged particles, you don't do astronomy. That's well known, because the highest radiation we've seen from the universe are actually protons and nuclei. And we don't know where they come from more than 100 years after they were discovered. And that is, of course, because they don't point back through the magnetic field of our own galaxy and the magnetic fields beyond our galaxy. So the solution to this is known since the 1950s. It's to do astronomy with neutrinos. And neutrinos are interesting because in this dark universe, they track the sources that produce the protons. You cannot produce neutrinos. Neutrinos come from decay of pions and kaons and such. And to produce these in the first place, you need a proton beam that you shoot on a target. This, of course, is a very fascinating problem. This dark universe is the place where cosmic accelerators live. And, you know, particles, we have detected particles like with an energy of 3 × 10⁻20th electron volts since the 1990s. And even before there was evidence. And Fermi had the concept of an accelerator that surrounded the Earth. This needs an accelerator that surrounds the orbit or tracks the orbit of Mercury. And of course, that's even when you use LHC magnets. And I don't think that's how nature does it, but we don't know how nature does it. In fact, there are so many ideas of how nature does it, but what you will see in this talk is that this one is slowly beginning to emerge. What this picture represents is a black hole at the center of an active galaxy. It's a galaxy that has an accretion disk. It's eating its own host galaxy. And particles are accelerated in the jets along the black hole's rotation axis, and also in the high field regions, which are above or below the accretion disk or the corona surrounding it. So there are well-established ideas how this could be the sources of cosmic rays, and this may be emerging as the answer. I leave the final conclusion up to you, but we'll find the answer eventually. So the connection, in case it was not clear yet, you accelerate electrons and protons. And when protons meet the intense radiation fields in the galaxy, in the host, near the black hole, they will produce pions, and the pions will decay into muons and neutrinos. And so this is shown here. It's just like you make a neutrino beam at a lab. Somehow the supermassive black hole accelerates the protons. In the nearby radiation, which is the target, you produce, by 1950s physics, charged pions and neutral pions. And so you produce neutrinos from decay of charged pions and gamma rays of actually 2 times the energy. And so that's the concept of multi-messenger astronomy. You cannot produce neutrinos without gamma rays of similar or even higher energy. And so this is the complete picture. And that's, of course, the picture of multi-messenger astronomy. Of course, the neutrinos are detected by IceCube in this talk, and the pi zeros, they will propagate in the microwave background, in other background field, possibly in the source, almost certainly in the source. I will come back to that, and emerge, be spread over the electromagnetic spectrum. IceCube is simple to introduce. We know actually how to build a neutrino detector. You need water and photomultipliers. And the problem with this beautiful experiment, it's a much better experiment than IceCube, it's 10,000 times too small to do neutrino astronomy. And we know that now. We weren't sure before, but now we know. And so the idea of how to build a huge detector is to use a transparent medium like deep ocean water. That idea was born in 1960. And you build a Cherenkov detector. You for particles coming through the Earth. They are neutrinos, nothing else gets through the Earth. If it's a muon neutrino, it can interact near your detector, make a muon. This muon travels for kilometers. And when you measure its Cherenkov radiation, it gives away direction, and it gives away the direction of the neutrino. All this is standard model physics, no ambiguities. So IceCube built such a detector, but instead of building in the deep ocean, it built it 1.5 kilometers below the South Pole. This is the geographic South Pole in the picture on the left here, exactly where this arrow is. This is the NSF station, which makes this project possible. And this is the IceCube construction site. And you see here this building, IceCube Lab, that's where the data acquisition and the electronics is. And if I show the IceCube Lab again, you see if you go 1.5 kilometers deep, then there is a hexagonal kilometer cube of natural ice that has been transformed into a Cherenkov detector. You see a few pictures of how this is done. Hot water drilling, change the ice. You don't make a hole, you change the ice into water. That lasts for about 30 hours, and then you put in photomultipliers encased in pressure vessels, which you see on the top right. And the photomultipliers are conventional 10-inch, 20-centimeter photomultiplier tubes. You build that experiment, and what do you see? Every year you detect about 100 billion cosmic ray muons made in the atmosphere, 3,000 per second. We detect atmospheric neutrinos from wherever in the Earth, and about, in fact, well over 100,000 every year. We do other science with that, which I won't discuss today. And we now know that we produce, for these numbers, about 120 cosmic neutrinos. 12 of these are above 100 TeV. So this is the picture, which may be useful for the rest of the talk. In fact, this is a picture I took for one of the last talks before we actually discovered cosmic neutrinos. You see here, this is the atmospheric background. It is well measured, well understood, can be calculated, and it prevents you from doing neutrino astronomy. However, this background disappears, even in a kilometer cube detector, at around 100 TeV. And if you build a kilometer cube detector fully efficient, then you will see all these predictions theorists made. And in fact, in 2013, in the first 2 years of data, we discovered this flux, which I will discuss further on. By the way, let me point out, I will always show energy flux, not particle flux. So E squared times the flux, what astronomers call nu F nu. And when I say it's very well understood, it's also very well measured. The water experiments that are under construction now in Lake Baikal and in the Mediterranean, they have measured the same flux. And here you see a comparison of these measurements. As it says at the top of my slide, this is of course a curse to have this huge background. On the other hand, it allows us to calibrate the detector and calibrate the energy measurement over more than 5 orders of magnitude. So I think we know how to measure energy, which is critical for the rest of the talk. So we discovered extragalactic neutrinos first in 2 ways. First, the same ways Super Kamiokande experiment would do it. You look for particles interacting inside your instrumental volume with no evidence of any particles entering the detector. I will refer to these as contained events. Here on the right, we do it by looking for particles that are coming through the Earth, which can only be neutrinos. For astronomy, this will be the workhorse on the right, because we can achieve resolutions at high energy of better than 0.4 degrees, to be improved soon. So this is a strange example of an event. It is superimposed on the data center in Madison, Wisconsin. And so you see the size of the event is 5 city blocks. You are looking at an electron neutrino that gave its energy to 1,000 TeV electron, and you're watching the Cherenkov radiation emitted by the electron shower. And the reason we can reconstruct such events is these events, as I said, it's 1,000 TeV energy. It has 300 sensors in it. The size of the sensors tell you how many photoelectrons are detected. That's a single photoelectron. These are many, many. In fact, in these 300 PMTs, the signal consists of 100,000 photoelectrons that we know to 2 nanoseconds. Easier to understand is a muon track going through the detector. And you see here, it comes through the Earth, and you see you follow the rainbow. It comes from an angle of 11 degrees below the horizon. And this neutrino has deposited energy of 2,600 TeV inside the detector. And in fact, we recently found an event with an energy of 5,300 TeV in the detector, which is by itself a 5 sigma discovery of cosmic neutrinos. Here is the event. They all look the same or similar. Conclusion, here is the flux. I show you first the flux of showers made inside the detector by electrons and tau neutrinos. And these are the data points. This is the flux detected using muons going through the Earth. I don't show you the data, I show you the flux with the error bar. Where does this flux come from? It comes from a measurement. In fact, I'll look on the right-hand side here. This is our measurement of the atmospheric neutrino flux with 8 years of data. And you see you need a cosmic component of cosmic neutrinos starting around 100 TeV as expected. You see the atmospheric flux disappear. And this is an 8 sigma measurement of the atmospheric flux. And so that flux is what was shown on this on this slide. So you see typically, this is, by the way, the background, which we reject. And you see it's consistent with a power law which has some power of 2.3, 2.4 for the energy flux. We actually discovered cosmic neutrinos 2 other ways. It's interesting to point out that if you see neutrinos produced very far away, they oscillate to equal flavors by the time they reach IceCube, roughly equal flavors. And that means that on this triangle, where this is the fraction of nu tau, this is the fraction of nu mu, this is the fraction of nu e, you expect the green point and you measure the black point with big errors, but we are working on an upgrade that will be improving this measurement significantly. And of course, the interesting point here is that if you don't end up in the right place, you have discovered new neutrino physics, which we know exist. You notice that there is evidence for a separation between nu e and nu tau, and you look at the nu tau candidates in our experiment. I'll show you the most spectacular one, of course. This is an event of about 100 TeV. And of course, when a nu tau interacts, it produces a tau, and the tau then decays. takes most of the energy of the neutrino and then decays in a huge shower. And so you can see this happening. If you look at the bright signals at the center, you see, look for instance in top right, you see the tau being produced and then the photons associated with the tau decaying. I already pointed out, you do oscillation physics at PV energy. The other interesting event is this one. You can actually produce neutrinos on an electron target. If you have a high energy anti-electron neutrino, high enough energy, high enough is in fact precisely 6,300 TeV, it interacts with an atomic electron and can make a weak intermediate boson, ATGF, that then decays hadronically. This is such an event. Our software reconstructed this right on the money. As it's most likely hadronic decay, you can look at the event as a function, at the photons as a function of time, and you see a big electromagnetic shower, but then you see muons outtracing the electromagnetic shower at the speed of light. Here, this happens in many digital optical modules. And so this is a tau that survived for 17 meters and then decayed. This is the cross-section for such an event. Of course, it exceeds at that energy the conventional production. And we expected in the sample, we studied 1.5 events and we saw 1. As we know the cross-section, we can determine the flux, and it's totally consistent, it's this point, with the measurements I showed before. The hard question was, where do they come from? And of course, since 2013, we have measured every trick in the book to answer that. We have used every trick in the book to answer that question and been spectacularly unsuccessful. So here you see a year of data. This map is completely uniform. And of course, it's overwhelmingly, the purity is 99% neutrinos, but there are only 120 cosmic in them. So this is 10 years of data. PowerPoint resolution cannot handle this, so I just show you the probability that there is a cluster of high energy neutrinos at any point in the sky. And the hottest point is this point, which coincides with the active galaxy, the Seyfert galaxy M77 or NGC 1068. We also search a list of 100 sources that pre-selected, and it's also the highest, the hottest spot in that list. So as the asymmetry in the map is only 3 sigma, we still quote upper limits, of course, which you see here for 2 assumptions of the spectrum of the sources as a function of the zenith angle. And so the reason the map is asymmetric for 3 sigma is that 4 sources stick out. In fact, M77 sticks out at 2.9 sigma even after the trials. Next one is TXS0506, about which you will hear later, but this has nothing to do actually with the multi-messenger event that I will talk about in a minute. And here the 2 other sources, these are active galaxies. And so you can play with this data yourself. They've been made public where I give the reference. So the question is, are these real or are they fluctuations? We know this one is real, but the others we are not sure. So we started a crash program to improve the detector, which we had not really done before. We improved the calibration and produced a set of pass-through data. We updated the reconstructions with the you know, most fancy new artificial intelligence method, our telescope was partially blind because we reconstructed the point spread function of the telescope by using Gaussians, which were approximate. So we cured that. We now have a well understood point spread function across the sky, and we are still improving the optics of the eyes. So you will hear about this very soon, and it will answer the question I just posed: are these fluctuations or are they real? I am going to skip this or going over it very quickly, but I told you there are inevitably gamma rays produced by along with the neutrinos. And these gamma rays, of course, you cannot stop the energy. I showed this picture before. These electrons will radiate and the gamma rays will further pair produce. So they produce a shower in the EBL, in the background light, mostly in the CMB. And then they arrive as many 10 GeV or so photons at Earth. That is if the source is transparent itself. Otherwise, they will lose energy in the source and come out at lower energies, which is typically the case, as I will point out. So they can be caught by Fermi, and you can do a simple exercise. Fit the neutrino data as e to the minus 2.15, take the pi zero corresponding to every pi plus, pi minus, dump them in the microwave background, and here is where they come out. So this leads to the correct conclusion that the energy flux in neutrinos and gamma rays is actually similar. Now you can fit this data in different ways and convince yourself you cannot avoid this conclusion. In fact, the data seem to indicate right now that the energy in neutrinos is higher than in gamma rays. Another way to see it is just to plot this energy flux, and you see it's similar to that in gamma rays and also similar to that in cosmic rays. And these neutrinos, by the way, as this shows, are not made by protons interacting on the microwave background. These neutrinos come from the sources. So here are our important conclusions. We observe a diffuse flux from the universe. We strangely don't see our own galaxy. We think we will, but we haven't reached 3 sigma. And the energy in the non-thermal universe is similar in neutrinos and gamma rays. So after trying to find the sources of our neutrino flux for a long time, we finally, in desperation, started sending alerts to the community. In other words, you detect an event, the data acquisition and the computers in above the detector reconstruct it, and without passing through the collaboration or even through the Madison data center, you send the coordinates directly via Iridium, via GPS, to all the telescopes in the world. And that worked. By the way, this whole sequence takes less than 1 minute. And so here on 43 seconds after this neutrino, which has an energy of 290 TeV that we detected on September 22, 2017, it was realized that there was a galaxy that was well known as a blazar by the Fermi collaboration within 0.06 degrees, and that it had been flaring for the last few months. By the way, this has a probability of being accidental of say 1 in 1,000 or so, 3 sigma. What makes this event real is what happened afterwards. A few days after this observation, the source was detected as a TeV blazar by magic. And we looked through our own data in the same direction and found this huge 2014 flux of neutrinos with an e to the minus 2.2 spectrum close to Eddington luminosity, and very interestingly, no gamma ray flare. In fact, I won't go into this, but it looks like there was no gamma ray flare at the 2017 event too. So this source somehow, when it produces neutrinos, is not a blazar. Because you have to realize the answer to the question of the sources is not these blazar GRBs. These sources are special. They are not an astronomical category because you need not only an electron beam, you need a proton beam. And if the proton produces a lot of pions and neutrinos on a target, the target must be opaque to gamma rays. At Fermilab, you don't get a photon beam that's accompanied by gamma rays. So we published these two observations, the multi-messenger and the IceCube follow-up. If you combine, they are statistically independent. You get to 4.2 sigma. You have to realize with IceCube, we can count our trials. We know we have no hidden trials. The question of what the source was elucidated, and why there were no gamma rays was elucidated by follow-up experiments. There was an optical experiment that actually watched the source within seconds after the alert, and it observed that the blazar was off, and that actually turned on 2 hours after the neutrino was observed. This associates the neutrino with the source independent time domain, independent of anything we did before. Interestingly, the images of the source made by radio interferometry showed that there was a powerful jet, and that this jet, after 5 milliarc seconds, very close to the black hole, lost its collimation, either interacting with intense fields or with something that was passing the beam. In other words, the image found the target on which the neutrinos were produced. And the two papers disagree on what this is. One paper argues it could be stars from the host galaxy passing through the target. The other, TXS, is a galaxy that's merging with another galaxy at the moment, and that through precession, the two jets crossed. This is an unsolved theoretical question. Let me skip this, but I have already told you all the sources from NGC to TXS, and what I'll show you later, have a hint that the source is modified and opaque to the highest energy gamma rays when neutrinos are produced, which is not a surprise. Here are these conclusions, and so I will just draw attention to this line. You can reach them. The stronger neutrino sources that we are seen by IceCube are more likely to be gamma ray obscured than not. You have to realize when a target absorbs protons to produce neutrinos, the opacity to P plus gamma is about 100 times smaller than the opacity to gamma. So these sources are going to come out at lower energies. We had another 300 TeV alert in 2019, which is shown here. It's a 300 TeV neutrino, and it's aligned with the blazar PKS 1502 plus 106. And it was there was a radio burst on top of the event, which was also the case with DXS. I don't have the time to discuss this today, but interestingly, if you look at the data of that source, the radio kind of tracks the gamma rays until at some point the radio flare starts, the correlation disappears, but look at the point a neutrino was produced, and there was a target to produce the neutrino, the Fermi flux goes clearly through a minimum, which is exactly what you expect from a dense target producing the neutrinos. I'm sorry, we have actually spent most of our time in IceCube, probably, looking for gravitational waves long between LIGO Virgo discovered them. But we have been unsuccessful so far. We hope to see neutron star merger. There has only been one, and the jet was not pointing in our direction. So we'll have to wait on that one. But of course, this is one of our high priorities. Let me conclude. The most important conclusion is that unlike in 2012, before we start running the experiment, we now know that neutrino astronomy exists. As clear from this talk, we meet more neutrinos with better resolution. New detectors are being built. IceCube is being upgraded and will build a larger detector. There are two efforts in Baikal and the Mediterranean that I already mentioned. But the important thing is that we have the feeling that we finally have the tools now through multi-messenger astronomy to identify the sources. Thank you very much for your attention, and thanks to my collaborators, but I prefer them this way. And
thank you very much, Francis, for this very, very, very beautiful talk. And see this latest data of uncorrelation with the JEV. But I enjoyed very much, and I would like you a favor to send me this picture that you have with a black hole and the neutrino detector on the Earth. One of the figures you have used, because I would like to borrow from one of our discussions during a Friday meeting.
Can you send me the number of the slide?
Well, the one that you have, just I cannot see now, but the one that you have, the active galactic nuclei and the detector.
Okay, I will look for it.
There is a beautiful, beautiful picture which I would like to use, if you don't mind.
It's a pleasure. I'll send it to you. Thank you.
And very, very, very impressive. And we are learning more and more. And I think the most spectacular result of this meeting is to see how quickly in these last months and not year, but months, the frontier of knowledge is progressing. And I think this is, your talk very well represents also this aspect. You are not new to the Grossman meeting, but this one was really to show how the frontier moves forward very fast. Thank you very much again.
Thank you.
I don't know if there are other questions, but maybe we are late in the evening in Italy, and even if you are early in America, and if there will be questions, we will send to you.
Yeah,
now,
I can also look on the web. Thank you.
Okay, thank you so much.
Thank you.